Okay, and then if anybody has questions, you can go down to the bottom and there's a chat button and you can type it in. My plan is that we do have about 4 speakers. They will be speaking for, some of them range for about 35 to 45 minutes, maybe a little bit longer. And in between, I am hoping to have the ability to do some question and answers. And if you need to get a break, go get a drink of water, run to the restroom, whatever it may be, that is, we'll have time to do that as well. So like I said, we'll try to do all the questions in the chat at the very bottom, and then after the presentation we can go through and answer those questions. And like I said, if you need a break, we can do that. Otherwise, I will just leave it to B. She is up first, and I will make her a host so that she can share her screen if she needs to. And I appreciate y'all coming, and I appreciate y'all helping me out with this, and I hope y'all learn a lot.
Thank you, Jamie.
You're welcome.
Thank you for organizing this, and thank you for the opportunity. So can you see my screen now?
Yes.
Great. And I believe I would be able to see the chat.
Okay.
Because that's how I figure out to do. I look okay now, so I just close it up. But I will pull up the chats at the corner. So if anybody have any questions or comments, feel free to use the chat as Jamie said, and I'll be able to see it. But if I got too excited and I don't see it, Jamie, please just let me know whenever there are questions, but I could not see.
Perfect.
Thank you for everybody joining me this morning. And my name is Bizhen Hu. Let me change the pointer so you can see the mouse. Yes. So I'm very new to Stillwater. I joined OSU beginning of this year. So now it's a little bit over half a year, but I'm still learning everything about agriculture here. Before I joined OSU, I worked in Georgia. But now at OSU, my position is about small farm, urban horticulture, and focus on vegetable production. I have 75% teaching and 25% extension. So I teach courses mostly in the spring and fall, and in the summer is really my extension time to do a lot of workshops like this one. And I'm so glad to be here today, and we are going to talk about irrigation methods for vegetable production today. So just give you a big picture of what we are going to do. I want to first share some background information so we have the knowledge to understand the irrigation methods we are going to talk about later. But first, I want to talk about the water status in the soil and the water in the plant. So these two topics are kind of the background or the basis for us to understand irrigation. And then we will talk about irrigation, the really core contents for today's talk. I will explain the water quality for irrigation, and then irrigation scheduling, including the amount of water to apply and the timing of irrigation. Lastly will be the irrigation methods. Okay, so this is the big picture. And now let's start with water status in soil. Even before that, let me just ask this question to start. Why we care about irrigation? Why we need to have irrigation for vegetable production? If you look at this map, the first map, this is how much rain we get in Oklahoma and in a yearly basis. And you can see by this color code, all of the areas in the state have, or at least most of them have, above 20 inches per year. And based off the general rule we get, We know most of vegetables, they require about 20 inches per season. So it means most of the areas in the state, the rain will provide enough water for the plants to grow. It seems like that. However, if we look at this second graph, this is the like the history of how much rain we get per year in the past over 100 years. And you can see how much it fluctuates here. We get these dry years, the yellowish or grayish color, this means drier years. And the green color means the wetter years. So what it means here is how much rain we get throughout all these years does change a lot year over year. So it's not consistent. And I believe you all know that even when we look at just 1 year and throughout the different seasons or different months, different days, the rain we get is really very inconsistent and it's not predictable and it doesn't really listen to us, to our wish. The rain will not always come when we need it or when the plants need it. And that's why we need irrigation. We cannot just rely on the rain. But I think today we have the whole section is a great topic. It's about rain gardening, rain collection, how to use rain well. And that is great. That's the natural resources we get. But at the same time, we also need to know we do need to provide irrigation to a lot of vegetables for them to grow well. Just because the rain is not consistent and not really predictable over the different seasons or different months when we need to grow a crop. So I hope this gives you a good reason to continue for this topic. Okay, then now let's look at the water status in the soil. This is the different thresholds of water or moisture level in the soil. And this is very important to understand because this really closely related to how much we should add water to the soil for the plant. The first extreme is this saturation point, the first image, the first graph here. This saturation point means the water filled all the space among the soil particle. And it means there's so much water that there's no air space at all. So this is full of water, but no air at all in the soil. It means the plants will have access to lots of free water. However, the water just push out all the air, so there will be no gas, especially oxygen for the roots to breathe or to respire. So that's the first extreme, saturation. The second one, the second picture, this is called the field capacity. And this situation is really the ideal situation because there's lots of free water for the plants to have access to absorb. But at the same time, it's not full yet, so there's still air space. You see there's still air space here. So there's still oxygen, there's still gas for the plant to use. So this status is when the water can be held by the soil against gravity. This is the level of water it has at the field capacity level. And the third one is the other extreme. It's like the opposite to the saturation. This is called permanent wilting point, the third picture here. And this is almost completely dry. There's very little water in the soil. All the water left in the soil is very tightly bonded or attracted to the soil that is no longer available to the plant. And there's very little water left. So the plant has absolutely no water to absorb. And of course, without water, there's all this air space. So yes, there's lots of gases for the plants to use, but no water. So this is another extreme. So from here, you will see the plants will not like either extreme. The plants will like the field capacity when there are both water and gases. But when it's too wet, it means no gas for the plants. And when it's too dry, it means no water. So either way, it's good for the plants. The plants would not survive in either extreme. And that really gives us the clue for us to understand how much water we should add to the soil. We want to make sure there's available water to the plants. And now let's just talk about this first, the total available water to the plants. And how much water is available to the plants? The answer is anywhere between the field capacity and the permanent wilting point. It means beyond those water that is tightly attracted to the soil, beyond that water, all the other water is available to the plants. So any water beyond or the permanent wilting points is available, and that make up the total available water to the plants. And if there's more than the field capacity, the extra water will eventually drain out. So it will not stay in the soil forever. So we would say available water is between the field capacity and the permanent wilting point. And then there's another threshold, very important. It's called management allowable depletion. So that is usually the set points for us. If we use any automatic irrigation method, we will use this as a set point. We will want to maintain the soil moisture level to be above this management allowable depletion. And this means the lowest water content in the soil that the plants will still grow well. So if the water level is below this management allowable depletion, then the plants will start to suffer. And that's why we want to maintain the water level to be above this management allowable depletion. And what is that? What is the percentage? There's not a magical number because it really depends on the crops. Different crops will have different management allowable depletion. So from a lot of extension fact sheets, you can find the information for different crops to get that number for your crop. So from all these, the message here is we want to provide both water and air to the soil and to the plants. And we want to maintain the soil water contents to be above this threshold called management allowable depletion, so the plants will have enough water. Okay, but how much water we should add to the plants, to the soil, or how much water is available to the plants really depends on the soil type. And this is very important to know too, because we all want to have a magical number, so we remember that single number and then we know what to set. However, that's not that simple. Irrigation is so complicated because different types of soil affect the irrigation scheduling. It means different types of soil affects the water status. So even if we add the same amount of water to the different type of soil, the amount of water that can stay in the soil or can penetrate downwards into the soil is very different and different types of soil. Now let's look at this first table. This is the available water holding capacity based on the different types of soil. And you can see these numbers, but what it means is the numbers increase. When the number is larger, it means the soil can hold more water, because these numbers means the water holding capacity. So the larger number means the larger amount of water the soil can hold. And if you look at these different types of soil, you will see the silt or clay soil can have has a large number or much larger number of capacity compared to the sandy soil. Or usually the soil with a higher level of organic matter can hold much more water than the soil has a low organic matter. like the sandy soil. So that is important for us to understand, because the more water the soil can hold means the less frequent we should irrigate, since the soil can hold more water, so we don't have to apply water that often, but every application will require a larger amount of water for those clay soil or silty soil with a higher level of organic matter. And another feature of the soil type is the soil infiltration rate. And this means how fast the water will move downward in the soil. It's called infiltration rate. And if you look at this table, again with this number, you will see a very similar chance, but it's to the opposite direction. When the soil is like sandy soil or has lower organic matter, it will have a larger number of soil infiltration rates. It means the water will move much faster downwards in this soil. But in a heavier soil or like the silt or clay, it will has a much lower infiltration rate. And this also has a very important interpretation for us to understand how often or how much we should irrigate. So whenever we need to design the irrigation schedule, we need to first know what type of soil we are growing plants on. And we know the different types of soil really make a huge difference. All right, so you already started to feel the complex here. And that's why we talk about it today. We just talk about the water in soil. That's the first topic. I want to provide the basic information. And now let's move on to the second topic, also the basic information. That's the water in the plants. We know irrigation is so important because the plants require water to survive. And why? There are several different reasons. First of all, the plants are made up of water to a large amount. For vegetables, most of them has at least 80 and usually above 90% of the biomass of that vegetable plants is water. So water made up the plants. That's why they need water to survive. And it provides structure and supports. Just like this, this is just one single cell of the plants, but when you picture the whole plant, you can see, imagine when there's not enough water in the plants will look wilted, and that's because the water lose out from the plants, so the plants shrink. And that's why water is important to provide the structure and supports for the plants. And it's also very important for all those biological activities in the plants, like you may heard about the photosynthesis and the plants growth. It all require water, because again, the plants grow, it means they get bigger, and that's because they keep more water inside, and the water get into each cell to make the cell expand, and then they can maintain their structure, and they become larger. So this is essential for the survival. And water is also required for nutrients and metabolites transport. So when we provide fertilizer to the plants, how can the plants get that fertilizer, get that nutrients? It's from water movement. And water is also essential for temperature control. And this is like us, when it's hot, it's going to be warmer later today. And if we go outside under the sun, we will get warm and we will sweat. And that's the same for the plants. When the plants are warm up, they will also sweat, and they need water. Sweat means water get out from our body. And the same for the plants. The water will evaporate out from the plants to cool themselves down. So it needs water to control the temperature, to sweat and to cool down, especially in the summer like now. So all these are the reasons the plants need water. And how can the plants uptake or absorb the water is, you may already know, it's from the roots. So it's the roots in the soil, that is the location where water enters the plant, or where plants get water. Then once the roots absorb water, let's look at this second, this picture. So we just say the roots absorb water, and then what happens next? The water will be moved upwards throughout the whole plant, and then evaporates out from the leaves. And this whole process is super important for us to understand too, because this is how the materials transport throughout the plant. We say water is so important, it's essential because it's the way how materials can transport throughout the plant. So you can see in this image, as the water moves through upwards from the roots to all the way up to the top of the plants, that's how the nutrients, the fertilizers, is transported into and throughout the plants. And how can these happen? How can the water draw upwards and transport and move throughout the plants? The force is from a process called transpiration, and this is a big word, but it's easy to understand because transpiration is just like sweating in the plants. As I just said, when it's warm, the plants need to sweat just like us. And what is sweating in the plants? It's called transpiration. It means this purple color arrows here. These represents transpiration. The water evaporates out from the leaves to the air. It's called transpiration. And this is how the water can move upwards. It's because the water loss from the top of the plant, and as the water move out, it will just like drag the next water, and then it's forming this force to pull up the water from the roots all the way to the top of the plant. And while we are talking about that, this is important for us to understand how we irrigate, provide irrigation. But first of all, I want to say, when we try to understand or schedule or apply irrigation, we always want to have this in mind. This is called the soil-plant atmosphere continuum. It means the water status in the plant is not isolated. We always need to connect the water in the soil with the water in the plant and also the water in the air. It's all in the same system. And that's related to the irrigation when we need to make that decision. Okay, so remember this first. So we need to always think about the soil, the plant, and the atmosphere as one whole continuum when we manage the water for the plants. Now, then we are ready for the irrigation. Okay, so we just talked about water in the soil, water in the plants. That is the first two topics to cover the basics for us to understand irrigation. I want to just have a quick pause and see if you have any questions. And those are very basic things, but they are all related to what we are going to talk about irrigation. Any questions so far about the water in the soil and water in the plants? All right, it means we are good, right? So now let's move on to irrigation, the topic for today. When we have the different water status, the plants will respond differently. So when it's too wet, that is not good for the plants because there's not enough oxygen in the soil for the roots to breathe. Then it will really cause lots of problems. First, it can easily cause the root rot issue because when the roots suffer, it will be very susceptible to the pathogen. It can also cause this soil crusting issue because when it's too wet, the algae can form at the surface of the soil, and then it will create this like crusting layer, and then it will make the irrigation much more difficult in the future. And when the water is too dry, water level is too dry, or there's not enough water in the soil, the plants will get wilted, as you all know. So for irrigation, it's really about balancing the air and water level in the soil. That's all irrigation is about. We want to balance air and water balance by a good irrigation scheduling. Then how to do that? For a good irrigation management, you may heard about the 4 R's for irrigation, or for nutrients management. Is also we can also summarize by these 4 R's. But these 4 R's are really a good guidance for us to have a good irrigation management. The R's means right material, right rate, right time, and right place. And this is a summary of irrigation program. Now, when we say right material for irrigation, it means the water quality, because material for irrigation is really the water. So the right material is a high quality of water source. And right rate of irrigation means the right amount of water to apply. Right timing means the timing of irrigation, when we apply that irrigation application. Right place really means the methods, how we apply the water to the plants. Okay, now we are going to look at them one by one in the rest of this talk. The water quality, let's start with the right material water quality first. So water quality for irrigation, you may wonder, what does this mean? It means before we use any water source for irrigation, we really need to understand that whatever water we use, we really need to know what is in that water. Is it safe for my plants? That's water quality. So the suggestion is always to have a water test before you use any water source for irrigation. From the water test, we will know what is in the water, and we will make sure the water is safe, is good for use of as irrigation, and it's good for the plants. So this is one example from, I get this from our fact sheets, but you can, if you find water quality for irrigation, you can find our OSU fact sheet, and you will get more details from that fact sheet. But this is an example of the water test results. So if you send your water sample to the lab, at OSU we have the lab, or you can work with your county extension office, and they will help you too. But once you send the water sample, you will get this type of result. And in the results, you want to pay attention to these, especially these 5 indicators. The EC, that's how it will show in the water test result. And that is really the electrical conductivity. And what does it mean is the total amount of salt in your water. And why this matters? The total amount of salt is really the salinity of your water source, and that will affect the health of your plants. Because if there are too many salts in your water source, then the plants will have to spend so much energy, or it will be more difficult for the plants to absorb water from your water source, because the more salt means the lower water concentration. That's how I always say it, in the water source, and the plants will have to do more work to extract that water from your water source and get that water for its use. So we don't want too high of salinity in the water irrigation for irrigation, and the threshold is 750. So you can look at your results and see whether you have too much salt in your water source or not. And when it's too high, when it's above 750, it can start to cause problems in your plants. So sometimes you may see plants look wilted, even when it's wet, when you provide enough water to the plants, but it's still wilted. And there can be different reasons, but one can be disease, but another reason can be too much salt in the irrigation, in the water you use for irrigation. So even there's water there, it looks wet, but because there are too many salts, ions in the water, the plants find it so hard to extract that water, to get that water into itself. So the plants still look wilted. And there's another term called fertilizer burn, the same idea. When you put too much fertilizer in the soil, and even if you have enough water or the soil looks wet, because of all the fertilizer salts in the soil, the plants cannot uptake that water and it will still get wilted. The same idea. Okay, so that is the first indicator you would want to look at from your water test results. The second one, this is the total sodium level. SAR is the sodium, how much sodium in the soil. And the problem of sodium is when it's at a higher concentration, it will become toxic to the plants. That's why we want to make sure it's not too much, and the threshold is 6. You don't need to remember all this because the threshold, because it will come with your water test results. But this is how you read this table. And another one very similar to sodium, I'm going to jump to this chlorine. It's similar to sodium. The reason we want to look at this is the same. If the concentration of chlorine is higher than 92, the threshold, then it will start to become toxic for the plants. That's why we want to make sure there's not too much of sodium and chlorine in your water. Another one is boron. Boron, you may know, this is an essential element for the plants. It's an essential nutrient. So the plants require boron to grow healthily. However, they are also very sensitive to boron. So at a very small concentration, the plants will start to show damage because the boron, when it's above 0.775 ppm, it will become toxic to the plants. That's why we call the boron is one of the micronutrients. The plants do not need much. It's essential, but the plants really don't need much. If there's too much, it will become toxic. The last one, RSC, means residual carbonates. And the reason we look at this is it's linked to the sodium. So when the residual carbonate is too high, then it will worsen the sodium issue. So it will bond to this, and it will make the sodium ions at an even higher concentration in your water. So we want it to be lower than the threshold also. Okay, so this is just the beginning for you to think about the water quality, but I think if you remember after this talk, water quality is very important for irrigation. And before we even use the water, we want to make sure the water source we want to use is safe. So we want to do a water test as the first step. And you will understand how to look at this. And if some of these indicators is beyond the threshold level, then you will want to have some action or water treatment before you use it for the irrigation. Okay, so that is water quality. Do you have any questions? Water quality is the first R. We just talked about the right material. Now let's move on to the second R, is the right amount or the right rate. Amount of water for irrigation. This is very important and complicated. How can we know how much water to apply? How much water is right for our soil, for our crops? There's not a magical number here again. And there are many different ways to determine how much water is the right amount of water. One simple rule you may already heard about is 21-2 inches. What it means. For most of vegetables in their growth cycle, they will need about 20 inches of water. And then at different time of the year or different seasons, because of the weather, for most of the months, they will need about 1 inch per week. But in the summer months like July, August, because it's warmer and more evaporation will happen to lose water from the soil, then we need to apply 2 inches of water. So this is like a general rule to know how much water is right. 20 inches for the whole growth season, and then 1 inch in the other months, and 2 inches in July and August. And that is a good start. However, we know it's more complicated because the different soil types affect how much water the soil can keep in the soil, and how fast the water will move downwards in the soil. So the different soil type will also affect how much water we should apply to your crops. And then the different crops also require different amount of water, and even the different, for the same crop, different growth stages also affect how much water they need. So this it's a long story, and we don't have a lot of time today to touch all those details. But to start with, you will need to know it depends on the soil type and also the crops types. And the last, of course, it also depends on the weather, how much rain we get, and how much sunshine, how much wind, temperature, humidity. Those also play a very important role in determining how much water is right. Like when there's a lot of rain, of course, there's already enough water in the soil, maybe too much already in the soil, then no need to add any. When it's sunny and at a higher temperature, you know there will be more water loss from the soil through evaporation, then we need to apply more water back to the soil. So all those are just some simple examples, but you know all these factors will work all together to determine how much water is right. And then now you will see that is a lot to consider. That's so complicated. How can I put all this into a formula and know how much water and get a number how much water to add? That's so complicated, right? Then the next question is how exactly we can determine the right amount of water to apply for irrigation. There are many different methods to determine the right amount of water. And I'm going to show you from the simpler one to the more advanced ones. The first method, you may have been using this method already, is the field or appearance method. It's by grabbing a handful of soil or medium you use and squeeze it in your palm. And then if there's no water drip out from your finger, then it means and the soil can stay together into like a ball, then it's enough water and it's the right amount of water. But if there's water drip out from your finger, it means it's too wet. If the soil stay loose, it cannot form into a ball, then it's too dry and it's time to add water. So that is the simplest I know methods I know can tell us whether there's enough water in the soil, whether it's too wet, too dry, or it's just right. But this is not precise. It just gives us a very rough idea of whether it's time to add water or not. To make it more precise, we can use some kind of sensor and get some numbers, and based on the numbers, we will know how much water is needed to determine their right amount of water to apply. So one measurement or one type of sensor we can use is based on the crop. We can measure the temperature of the leaves, so that is called the crop indicators, and that is related to how much water the plants have, and that's related to how much irrigation is needed. The other measurement is called evapotranspiration, and that is the measurement of how much water is evaporated out from the soil and how much water is evaporated out from the plants. So this word is like two portions of it. The evapor means evaporation out from the soil, and transpiration, you may remember I said transpiration is the evaporation of water out from the plant. So by combining the evaporation of water out from both the soil and the plants, we will know how much water in total is lost out from the whole system. Because I said when we look at irrigation, we need to look at the plants, the soil, and the air as a whole continuum. So we need to measure how much water is lost from the plants and from the soil. And that amount of water lost from the plants and the soil is the amount of water we should give back to the system. Okay, the last one is to directly measure the soil water content. And there are a lot of sensors to do that. And I list a fact sheet here. These two fact sheets have a lot more information and shows the different types of sensors we can use to test or monitor how much water is in the soil. And based on that amount of water in the soil, we can determine how much water we should add to the soil to make it the best for the plants. And I mentioned the manageable level. That threshold can be set and links to the sensor and controller. And then the sensor will sense how much water is in the soil. And when that water level hits the threshold, goes lower than the threshold, then the irrigation system can turn on automatically by the control. So then in that way, we can have an automatically controlled irrigation system. And this picture just shows us one example of this sensor and control system, but there are lots in the market. So you can see how much water to apply really depends on lots of factors, and how to know how much water to apply is really complicated, but there are different methods we can rely on. We can use the simplest one. It's easy and it doesn't take any equipment. It's very inexpensive, but we can also invest in some sensors, equipment, or even control to make the irrigation very precise. So we will know we provide the right amount of water to the plant. Not too much, not too little. All right, so that's amount of water. And the next is the timing of irrigation. I think I may have to speed up a little bit because I already used 30 minutes now. Okay, so I will speed up a little bit from now on to finish this. So the timing of irrigation is also depends on a lot of different factors, just as the amount of water we should apply. It depends on the growth stage of the plant. So this table shows the different growth stage of different crops. And you can find this in the vegetable crop handbook. And you can download this handbook for free from the website. This is very, very good information, very practical. And what it means from this table is for different crops, it has this essential or called critical period. That is a time of the plant's life when adequate water is so essential for us to have a good crop or have a high quality of products to harvest. So if we need to focus on a specific time to provide irrigation, that is the time we should make sure there's enough water to the plants. Different crops have different critical periods for irrigation. And it also depends on the time of the day when to apply irrigation. And the general recommendation is we want to apply or want to water in the morning. The reason is we don't want water stay in the leaves for a long time. That will really create the right condition for disease to develop. That's why we want to water in the morning, and the plants will dry out very quickly, so the plants will not have wet leaves for a long time, and that's the way to prevent diseases. And how often we should apply the irrigation, that's really affected by the weather, the type of soil, the different crops, how much water they use. All those will need to be considered. So we need to go back to what we just talked about, how to determine when is a good time to apply irrigation, when it's too dry already. We can use different methods, and we can use a sensor to monitor how much water is left in the soil. Then we can decide it's time to apply water again. Okay, so that's the timing. Then the last R is the right location. And that's related to the irrigation methods. How exactly we add water to the soil. That's called the different methods. And there are 3 common methods. One is surface irrigation, and the next one is overhead irrigation, or you may call it sprinkler irrigation. And the last one is drip irrigation, or it's also called as the trickle irrigation. So these 3 different methods of irrigations are the very commonly used ones for vegetable production. And if you look at these pictures, you can see how these different methods deliver water to the plants. The first one and the last one, the surface irrigation and the drip irrigation, both deliver water from below the foliage. So you see the surface irrigation, water is delivered from the base of the plants, and it doesn't wet the leaves. The last one, drip irrigation, is the same. Water is delivered to the soil directly. It doesn't wet the leaves. But the second one, overhead irrigation or sprinkler irrigation, the water is delivered from above the leaves. So it will wet the leaves. And this is important for us to know because this is related to disease management. Now let's look at each method for more details. The surface irrigation, you can see this picture again. We need to dig these rows and lead the water from the water source to each row of the plants. And the water is delivered to the plants from the base, below the leaves. The good things about this irrigation method is it's very simple. It doesn't require special equipment. It doesn't require special techniques or not a lot of new skills. So it's simpler and it's less expensive. So it takes smaller capital investment at the beginning. And once it's set up, it takes less maintenance. So once this is dig, the water will be delivered from the water source, and that's done. It doesn't need a lot of follow-up maintenance. And this is also less sensitive to the weather. Like when it's windy, it doesn't really matter. The water will be delivered to the plants as the same and very evenly. And the water quality is less as an issue. We talk about water quality at the beginning. For these methods, it doesn't have the tape or the small pads for irrigation. So the water quality is less of a concern for this method. But there are disadvantages of this method. It's less efficient because the water is open to the air. So you will imagine there's a lot of evaporation from the water from here, from all these irrigation rows, back to the air. So it loses a lot of water in that way. So a lot of water is not used by the plants. And it also takes a lot of labor for operation. For the beginning to dig these holes and lead the water to the holes, that takes labor. It also requires land grading in your field, and that is not always true for the field. It can have a big slope, and this is difficult to set up. So it needs land grading to set up this system, and it requires lateral spread of water. So the water it's delivered to the row, but it requires water to spread in a lateral direction, so it will get to the row of the crops, into the roots of the crops. If we look at this picture again, the water needs to spread in a lateral direction so it can get to the row of your plants, of your crops. But how does the water spread out in the soil really depends on the soil type. And if the soil is the clay or loam or has a higher level of organic matter, it can spread more wider or in more in a lateral direction. But for sandy soil, it really infiltrates very quickly downward, so it doesn't spread out a lot. And again, this means whether you can use this method well, it depends on the type of soil you're working on. So the most application of this method is for fields with smaller ground slope, because it needs a relatively flat surface, or it would take a lot of work to do the land grading if you have a huge slope. And it works better for heavier soil texture like clay soil, so it has a better lateral spread of water, so the water can move to the crops. And it requires the location has a large water supply and flow rates. Then now let's look at the second method, overhead irrigation. It can look like these two pictures. So the overhead irrigation means water is delivered to the crops under some pressure from different types of systems. Like the first picture, the sprinkler irrigation, it's fixed here, so it's not moving. But the second picture, this is a central pivot system. It's constantly moving. So it can be fixed, it can be moving. And the good things about this overhead irrigation system is it can be applied at a lower rate, and you can control how much to apply. It can be automatic. You can just hook it up with a timer to control how much irrigation to apply and how long and when in a day to apply. And it can also combine with fertigation and chemigation. It means you can hook up with a fertilizer injector or connect with a pesticide application. So the irrigation can be combined with nutrient management or pest management. And this method can be also used to protect plants from heat or cold. For heat, when it's warm outside or when it's too warm for the crops, you can spray water using this overhead irrigation system. And once the water gets onto the leaves, it will evaporate out back to the atmosphere. And as the water is evaporated, it will take the heat from the plant. And that's how we can protect plants from heat using this method. And then for cold, it's very similar. We use this overhead irrigation to apply water to the surface on the leaves. And that needs to be done right before the temperature gets down to the freezing point. And then once we have water on the surface of the leaves, the temperature drops, the water will change from the liquid form to the solid form. So it gets frozen, the water gets frozen. And once that happens, it will release heat. So it means when water changes from liquid form to becomes solid from when it become when water change from liquid to ice, it will release heat, and that heat can protect the plants from cold weather or a low temperature. And this is very commonly used for crops like strawberry, blueberry, and you may already use it. So that's a good thing of this overhead irrigation. But there are problems of this method. Giving the water from above the leaves can wet the leaves, and that can become a problem when we have some disease issues and they favor wet condition or high humidity condition. Then if we make the leaves wet, it will be easier for those diseases to develop. And that's why if we use this method, we want to apply this overhead irrigation in the morning so the wet leaves can dry out as quickly as possible. Then we can reduce the risk of having the disease developed. And when it's windy outside and we use this overhead irrigation, the winds will make a problem. The irrigation will become less uniform over the field. And I said this overhead irrigation is applied under certain pressure, and we need to be very careful about how much pressure we use. Under lower pressure, the droplets may become too large. And then the big droplets of water can destroy or damage some of the crops, especially when the plants are just transplanted or when the plants are just emerged, they are very small seedlings, then big droplets can damage those small vegetable seedlings. And we also need to control the application rate to prevent runoff drifting. So it has more maintenance to be done, and need to have an eye on the pressure we use for this system. The last method, this is the last two slides I have. The last method is drip irrigation. This is very commonly used for vegetable production. It has lots of benefits. So I use this chart to show you what it means by drip irrigation. This is like a common setup of drip irrigation. It has the water source, use a pump to deliver the water. And it also have this vacuum breaker at the beginning of the system. It has this backflow prevention valve. Both the vacuum breaker and the backflow prevention valve is here to prevent contamination to the water source. So especially if you hook up this system with a fertilizer tank, so you combine the irrigation with fertilizer application, then if there's some issue in the pressure or if you have a power shortage outage, then the irrigation can go back to your water source and cause contamination and bring those fertilizers to your water source. And that will become a problem. That's why we need this vacuum breaker and the backflow prevention valve to be here to prevent the problem. When when you turn off the system or when there's a power outage, when there's a problem in the pressure, the water with the fertilizer will not be able to go back to your water source if you have this vacuum breaker or if you have this backflow prevention valve should be set up here at the front. And then again, you can hook up with the irrigation with the fertilizer tank, so you can apply fertilizer to the system as the same time as you irrigate. And the system will go back to go out to these smaller drip tanks, and then it will be delivered to each individual plant. And in the drip tanks, there will be emitters to control how much water to be provided to the plants. So this is the whole systems of how it looks like. Then if you compare this system with the previous two we just talked about, the advantages of this drip irrigation is it's more efficient. The water is delivered to the root zone directly, so it doesn't have a lot of evaporation back out to the atmosphere like the surface irrigation. And it's very uniform. It doesn't matter whether it's windy or not, like the sprinkler irrigation. If it's windy, the irrigation will become less uniform. But this drip irrigation doesn't have this problem. And it can prevent disease because the drip irrigation doesn't make the leaves wet. So that can make a big difference in the disease prevention. It can also control weed because the water is directly delivered to the root zone. It doesn't make the whole field wet. In that way, when there are no plants, there's no water, so it will prevent the weeds developed. It can also limit the overuse of agricultural chemicals like fertilizers, pesticides, and it has a very precise control of how much you add to the system. And it's not add to the whole field, but just to each of the plant root zone. That's why it will prevent the overuse of these chemicals. And it doesn't take a lot of labor to operate. Once this system is set up, you just turn on the valve, turn off the valve. Very easy to operate. And it can be automatically controlled. You can hook it up to a timer to control when to turn it on, when to turn it off. And it's very precise how much water, how much nutrients or fertilizer you add to the system. So because it doesn't take a lot of labor, it has lower operating costs. Compared to that, the surface irrigation, it takes lots of operation, take lots of labor, but this one doesn't. But it also has some disadvantages. It takes higher initial investment costs. The system does cost more compared to the many of the overhead irrigation system, or compared to the surface irrigation. This takes a lot more investment at the beginning, and it also require more management and maintenance. It requires more skills and new set of techniques to maintain the system. And the water is delivered to the plants directly, but it means there's less soil water reserves for the plants. And the moisture, it stays in a smaller area of the root zone, so it has less moisture distribution among your field. And this method is most commonly used for fruit and vegetable crops. It works very well with mulches, and it works for sandy soil, and it's best for the high value crop because of the high initial investment costs. All right, so I think I used over more than 45 minutes, but this is all I have about the irrigation methods. And please feel free to let me know if you have any questions. I have my contact information here, and I'm very glad to share the time with you today. Thank you for your interest and attention.
Thank you, Bea. That was great. Does anybody have any questions? All right, if we don't have any questions, then we will go to Jason Vogel. Let me see here. Sorry, I'm trying to figure this out, Jason.
No worries. It looks like it's letting me share my screen, so we should be good.
Okay, great, great. That was what I was trying to let it do, but
Okay, are we ready?
yeah.
All right, very good. Well, thank you all. I'm going to move my camera over here so I can see my presentation and look at the camera at the same time. Let's see if we can get everything situated here. Jamie, thanks a bunch for inviting me, and I appreciate you letting somebody from OU be on this OSU Extension workshop presentation. But a little bit about me. I'm a professor in civil engineering and environmental science here at OU, and I'm also the director of the Oklahoma Water Survey. But I do have OSU roots. My PhD is from OSU, and I was on the faculty in biosystems engineering at OSU for 7.5 years before moving over to OU. While I was at OSU, I was the extension stormwater specialist. So I've done lots of presentations on this topic and others with master gardeners, and I really appreciate everybody's time. I think there's probably only 5 or 6 audience members. So since we have a limited number, I was kind of wondering if the audience members could just kind of introduce themselves and tell me what their interest is relative to rainwater harvesting, if that would be okay.
Yeah.
Feel free to speak up. Because I have my presentation on, I can't see everybody's name or anything on the participant list.
There we go.
I'll tell you that I'm Brenda Gandy. I'm an extension educator in Stevens County, and I just am particularly interested in harvesting all the rainwater that I can, because rural water to water my lawn is very expensive.
Very good. Okay, great. Jamie, maybe you need to call people out that are on the list. Like I said, I can't see the names the way I have the screen now. So
Yeah, that's a fine. Paige, if you want to unclick your microphone. If not, that's fine.
that's okay. I can get started too.
Okay.
Maybe folks don't have microphones on their end.
And they may not. I
Yeah.
don't know.
No worries, no worries. Okay, so that's great. But we'll go ahead and get started here. And I want to encourage everybody, especially with this small of an audience, feel free to interrupt me at any time. It could be in the chat, or if you want to just start talking. I know it's kind of awkward on Zoom sometimes. So if you guys have a question, it's better to get it out right away so you're not thinking about it for the next 4 slides and maybe missing something that comes next. So feel free to interrupt me. I will not be offended at all. So we're going to talk about another number of topics related to harvesting of rainwater, including benefits, the uses, and then really what are the parts of a rainwater harvesting system and how do we size it? That's really what the big bulk of the presentation will be about. So let's just jump right in here. Benefits, short-term benefits, you can save water for when you need it. It also, if you collect it in large enough volumes, it also reduces stormwater runoff and can help contribute to reducing of flooding. But it's also better for growing plants than tap water. It's slightly acidic. It's generally free from salts and minerals and other natural and man-made contaminants, including disinfection byproducts. And many gardeners that I've talked to, swear by using rainwater as opposed to tap water. Their plants just perform better. So that's really great. And then in a long-term benefit, it can reduce your demand on your infrastructure, energy costs, stormwater utilities. And it's also insurance for your plants during seasons of drought. I will say, if you're doing it to save money, in many areas, that will take a long time to get a return on your investment, maybe 15 or 20 years. On rural water districts, if water is more expensive, then you may get it back quicker. I worked with somebody who had a vineyard up in Wacomas one time, and in Wacomas, the water is the most expensive that I've seen in the state. I haven't seen them all, but it was pretty expensive. And he had a return on investment in about 5 years on a large system that was 14,000 gallons. So it kind of just depends on the price of water, but water is generally relatively inexpensive in a lot of places. So it's not necessarily just looking at return on investment from saving water bills, but there's a lot of other benefits as we've mentioned. So what can you use it for? You can use it for irrigation, and that's probably primarily what this audience is interested in, but also can be used in manufacturing processes. You can use it in your toilet, any non-potable type uses, watering your garden, washing down your yard or driveways and those types of things, or your car. And finally, as an emergency water source, and you'll see some forest managers and other things will collect that rainwater, intersperse it throughout the area that they manage, so that they can utilize that for fire prevention in the case of an emergency in really large volumes, obviously. So let's talk about the parts of a rainwater harvesting system. And this is probably the most important slide of everything that we're going to talk about, no matter whether you're using a small rain barrel or a 500,000 gallon rainwater harvesting system. You're going to have these types of parts to your system. And let's just start from the top as the water flows. First off, we have our catchment system. Generally, that's going to be a roof or some other type of impervious surface, some surface that the water will run off of, that you'll collect the water from. So like I said, a lot of times we're going to be looking at the roof. And then there's a conveyance system, something that moves the water off of that catchment area towards our storage device. So generally that's the gutter and the downspouts. And then there'll be some water quality improvement devices. And I'm not going to go into these very much right now, but later on in the presentation, we'll talk about this. And these can be optional, but they really, really help both improve the water quality and make it so you have to maintain the system, clean out the tank a lot less. And that's things like a roof washer and a first flush diverter. Next is your storage, and that could be a below ground tank or an above ground tank, a rain barrel, or a series of rain barrels. There's always going to be an overflow because you'll get bigger storms than you can handle. And we'll show how much water you can get. You can get quite a bit of water with a relatively small storm. So we always need to have an overflow so that water can go someplace so it's not doing any damage. And then finally, the delivery system. And we heard a lot about irrigation in the previous presentation. So some way to get the water to where you want to use it for. So those are all of the parts of our rainwater harvesting system, and each of them has a role. Each of them is very important. So one thing you want to think about is, what are my water needs? And just kind of put things in context, how much water is used for different things. So flushing a toilet, maybe between 0.6 and 1.6 gallons per flush, and that's getting better all the time as we have more efficient appliances. A washing machine will use 30 to 50 gallons per load. A dishwasher, 7 to 15 gallons per load. A bathtub, 30 to 50 gallons per use, right? A shower, 2.5 to 3 gallons a minute. So depending on how many minutes you're in the shower, that you can kind of calculate out what that would be. And then in your sinks, you're using a gallon to a gallon and a half per minute. But thinking about that, if you're looking at a rain barrel that holds 50 gallons, you're going to use this up for some of these types of uses really, really fast. And typical household water use is 50 to 100 gallons per person per day. These kind of uses are probably the second level after you start to use it for irrigation, and then you really get into it and you start to use it for some of these other non-potable uses. And you need to look at your local ordinances and things like that to look at those types of reuses, especially in things like toilets and stuff, but it can definitely be done. You usually just pipe it different with the purple pipes, so it's non-potable. So let's talk about agriculture. So whether you're talking about grasses or small vegetables, we're somewhere around 1/4 of an inch per day. It's going to be seasonal. In the winter, it's going to be less. In the summer, it's going to be more, which is 18 gallons per 100 square foot per day, around 20, and around 9,000 gallons per acre per day. So that's the amount of water that we need for irrigation. So that storage volume really makes it impractical to have this as your sole source of water, but as supplementary water, it's great, and we can get as much as we can. But if you're using this as your sole source, you really need to have some big tanks and be able to store that back for when it's dry for a long period of time, because you don't need it the day after it rains, right? You need it when it's dry. So we need to be able to store that. And another use that sometimes that I've worked with folks on before and isn't used quite as much, but you can use it for for livestock watering as well. And so beef cattle, 8 to 10 gallons per head per day. Calves are based on weight. Here's horses, sheep, chickens, 9 gallons per 100 head per day. These are average amounts once again, and it's going to be more in the summertime and less in the wintertime. Towards the end of the presentation, I have actually a couple of systems for harvesting rainwater for wildlife and for cattle that A&M came up with, Texas A&M, and I'll show you those. Those are pretty cool. So but the point of this is we use a lot of water, and so the bigger the system, the better, the more we can get benefit out of it, the better return on investment we're going to get, the sooner we're going to be able to make that even economically viable. So let's start at the next part, and that's calculating that catchment area, the part that it's running off of here, and how much water can we collect from that. So water is a volume. You're calculating that by a volume, and so that's going to be that area, length times width, times the depth of rainfall that you get on there. And then there's this other factor here that we also need to think about that's called harvest efficiency. So you're going to get a certain amount of rain coming onto your rooftop, but you could have a little bit of leaky pipes that could fall off the edge and not in your gutter, other types of things. So you're never going to get all the rain that falls on your rooftop. And a good system will get probably 90%, maybe 95% on something that's brand new and doesn't have any leaks. If it's older and has some leaks, or it's not quite straight and it runs off the other end, or other types of things, it might be more like 60 to 70%. So when you're thinking about the amount of rainfall that you can get, we need to make sure we're thinking about that harvest efficiency. So how much water can we get? This is the biggest question I always get regarding rainwater harvesting. So with 100% efficiency, 1,000 square foot roof with 1 inch of rainfall is 621 gallons. It's a lot of water. And if we're thinking about a 60-gallon rain barrel, 1/4 of an inch on 1,000 square feet can fill that up. So that's why I always stress to folks, if we can do something bigger than a rain barrel, it's going to be a lot more beneficial, and you have that potential to get that. You know, an inch over a whole acre is 27,000 gallons. So if you have a large yard and you're trying to give it an inch of water a week, that's 27,000 gallons. That's a lot of water. So one thing to think about when you're calculating that is it's the vertical projection, or if you think about the drip line on the eaves, it's that measurement. It's not measuring this length here on the diagonal times this length, because that's going to be different, right? This is our old geometry that rears its ugly head once in a while, thinking about this length is going to be shorter than that length. So here's an example of that with a pretty high-pitched roof, over 45 degrees, and you have 60 feet this way, 50 feet going up and down. If you measured it this way, you'd get 500 feet, but really our catchment area per side is half of that 30 times that 100, or 3,000 square feet on that type of a roof. So when we're calculating up how much water we can get, we need to think about that. So rainfall potential, this is a repeat of a presentation or a slide that was on the last presentation. But how much rainfall can we get? You know, really varies from west to east. You know, 15 inches of rain a year. Southeast Oklahoma, you know, 55 or 60 inches of rain a year. You can get a lot more there. You know, somewhere in the middle here, Comanche, Stevens County, 25 to 30 inches probably is typical, although in Oklahoma, typical never happens. But anyway, and then we also need to think about temporal variations, and when are we going to need it? So it may rain that much during the year, but a lot of times when we need it is when it rains the least amount. So when we're thinking about July and August, we only get 8% of their annual rainfall during those months. So if we're trying to store it from other times when it's raining more, back in May and June, we need to be able to have that storage capacity so that we can hold it back. And here's lot and rainfall. This is average rainfall per year, but you know, in July, 2.25 inches. May and June, we can get a lot more rainfall, but this is when we're going to need it. So we need to be able to store some of this so that we can use it down here. So let's talk about assessing our tank needs. First, we're going to start off looking at our catchment area, research your rainfall and what are your water needs. What do you want to use it for? Are you watering your garden? Are you watering your landscape? Do you want to water your lawn? Do you want to use it for other things like washing your car or your driveway, or even some non-potable uses in the home? And then from that, knowing how much you want to use, then you can size your tank to kind of account for all of those types of things. So as a rule of thumb, and this is just a rule of thumb, there's more precise ways to do this, but this works really well, is you find the month with the greatest difference or deficit between how much it's going to rain and how much water you're going to need for that use, and size your tank to account for that difference. So when you're using it for irrigation, generally that's looking at how much rainfall do you get on average in July and how much do I need to use? And if it didn't, and so then sizing your tank to make up for that difference in the month with the biggest deficit, then every other month you're going to have enough water, right? And so that's just a general rule of thumb. Usually works pretty good. So we're calculating this based upon, this is a unit conversion, this 0.6 times the amount of rainfall we get, times the area, times our harvest efficiency. And I talked about that you're never going to get 100% of the water off of the roof. I will say there is a OSU fact sheet that I wrote that's out there yet on rainwater harvesting. We also have a fact sheet with the Oklahoma Water Survey that's kind of updated from that, has a lot of the same information, but it's updated. That's also available on the web. So either one of those things will have a lot of this same information. So let's talk about the tanks, because we're moving from the roof down as the water moves. So we're going into the tanks. It can be above ground or below ground. Preferred materials, plastics, concrete or steel are really the preferred materials. Mostly you will see your poly tanks. You want to try to have smooth interior surfaces on your tanks. And the reason for that is the rougher the surface there it is, the more there is for the opportunity for algae to attach on the inside. You always want to use watertight, non-toxic joint sealant whenever you're connecting anything to it. And this is really important. We want to prevent mosquito and algae growth, and for mosquitoes specifically, we want to cover up all the openings. Never have an opening that the mosquito can get through. If it's below ground, you want to have a manhole to clean it out, and you need that to be greater than 24 inches wide. And you need to have at least 8 inches above the surface of the ground. So what that means is, here we have this clean out on our below ground thing. We want to have that at least 8 inches above the surface of the ground. There's a couple reasons for that. The practical thing is, if there's water running over the surface of the ground, we don't want it to get into our tank and contaminate. It could be washing fertilizer or pesticides off your yard or whatever. We don't want it to get into our relatively clean water that's in there. The other thing is from a safety standpoint, and this is also really important, if you have a plastic lid on that and it's flat with the ground and you have little kids running around there, and the lid can get brittle in the sun over the years or whatever. If it's flat with the ground, they could be running and fall right in, and you have this tank full of water underground that could be 4 foot deep, and it only has this little tiny opening on the top, and it can be really, really dangerous. Well, if it's sticking 8 inches out of the ground, probably the worst that's going to happen is they're going to run and trip over it, but they aren't necessarily going to fall into it. So from a safety standpoint, that's really important as well. On the below ground ones, or even the above ground ones, concrete can work really well, and sometimes you can reuse other things. Grog's Green Barn is a nursery in Tulsa, and they have some concrete rainwater harvesting tanks that they are actually recycled grease pit traps from an old restaurant that they utilize, and they're able to put 400 gallons into each one. And so So that can work really good. It's going to be solid. On the above ground ones, you want the outside to be at least opaque. You want it to be solid. You don't want it to be transparent. That's for their algae growth. If we get algae in there, you know, they need sun to photosynthesize and grow, but if we can block that sun, you're going to have less algae growing inside of it. So when we're locating our tanks, we want to consider gravity for delivery, but you may need a pump. If you're wanting to use drip irrigation, you're probably going to need a pump to get it up to the pressure that you need. B may have some other comments on this, but there are some low pressure drip irrigation systems that I've tried to test out and on rainwater harvesting, and I have never got them to work very good without a pump. So we need to, so if you're using drip irrigation, you probably want to get it up to the pressure that you need, because otherwise you need to have it up, you know, 17 feet in the air to get 5 PSI, which kind of doesn't work for rainwater harvesting systems. From a sociological standpoint, the closer the water is to where you're going to use it, the more likely you're going to use it. So if your water is if your rainwater harvester is way on the other side of the yard and your garden's way over here, but you can run your hose over really easy, you're not as likely to be able to use it. So the closer you can make your rainwater harvesting system to your point of use, the better. If you're in town, you want to think about homeowners association, deed restrictions, those types of things. I know in Oklahoma City, there's some restrictions related to grain barrels on the front of the house versus the back of the house. I'm not sure about Lawton or other communities in Comanche or Stevens County, but and HOAs may have some restrictions on that. So make sure you're thinking about that when you're putting those in. I helped install a few in Lawton, so I don't think that there's much of a restriction on the front of the yard, at least from the city standpoint. Some other things to think about as we're putting these in, especially if you're moving it from gutter to other places, we want to have our gutters 0.5% slope, so that's 1 inch per 16 feet. That's pretty common. Gutter hangers, so that we're holding it up. Expansion joints, if they're too long. These are things that the folks that, if you're having to add gutters to your roof, these are some things that they need to think about. How big does your downspout need to meet? So 1 downspout per 50 foot of gutter length and 1 square inch of downspout area per 100 square foot of roof area. So sometimes you might look at those downspouts, or maybe just me as a dorky water guy, but how big is that downspout supposed to be before, you know, for the certain size of roof? So if you have more draining to it, you're going to have a bigger roof. And that's kind of the general rule of thumb. If you are moving water horizontally, like from a downspout over to your tank, you're going to have a little bit more of a slope on that, because you don't want stuff to get stuck in there, clog it up, and then you don't get water to your tank. So that's a 2% slope. So that's 1 inch of fall every 4 feet as we're moving that out. If you have to move it a long ways, you want to have a clean out. So someplace where you can take off a cap or whatever and clean out that pipe. And then this last one is something that folks don't think about a lot, but if you're having to move it to turn corners, you don't want to use a tight 90-degree elbow, because that's a place where it can get really easily clogged. So you want to try to limit those pipe vents to 45 degrees, or they make an elbow called a long sweep 90 that is basically kind of like 2 45s together. And so it makes that going around the corner a lot easier, because you'll have a lot of water coming down when we get these gully washers. So those are some of the things to think about related to that. So let's continue to talk about types of tanks. Above ground, you'll have your polyethylene tanks, some liner tanks, and these get bigger and bigger. I won't talk about the big ones too much on this. And then below ground, once again, you have your poly tanks, concrete tanks, matrix box, which there's a nice example at the OSU Botanic Garden of this that Dr. Anella put in, fiberglass or a sand cistern, and we'll talk about that a little bit. And many years ago now, Kim Toscano did one of these on Oklahoma Gardening, and there's a nice set of videos from that out there on the web. So our poly tanks, our polyethylene tanks, are the ones that you're going to be most commonly looking at. You can come up to 10 or 15,000 gallons. Usually around $1 a gallon is the cost. The smaller they get, the more they are per gallon. As they get bigger, then it'll be less than that. You can put potable quality water in there. That doesn't mean that if water's in there, it's potable quality. If it was potable when it went in and it's clean, then it'll keep it poly. They are UV inhibited, and you'll see here, this is a green one that's very solid walled, and the sun can't get in there. So green or black are the common colors on that. They do come in a lot of sizes and dimensions and colors, and the more custom you get, the more expensive it's going to be. But I've seen them where they can be like even fence sections that they put in there, or other types of things. They're relatively lightweight and inexpensive, and they can be linked together. So even if you have rain barrels and you have a 60-gallon rain barrel, but you can link together 10 of them, and voila, you have 600 gallons of storage. So that's really great. The bigger ones that, if you're looking for much larger uses, some of these metal liner tanks can be utilized, or even the really, really big ones can be utilized for rainwater with concrete or other types of things. So the next one is our below ground ones. So once again, the polyethylene tanks, those are usually the same size, up to 10,000 gallons or so. They're going to be a thicker wall because they have to withstand the force of all that soil on top of it. It's going to be similar to what you'd see on a septic tank that you'd see at Lowe's or Home Depot or anything like that. They're relatively lightweight. The opaqueness of it isn't as important because it's below ground, the soil's blocking all the sun and that kind of thing. So it's dark, but it's going to be a little bit thicker walled in general. So our concrete tanks, and I mentioned the reuse of the grease boxes, but you can utilize concrete tanks or even pour your own concrete to make some of those types of things. I had a former student at OSU who went over to Sierra Leone in Africa for 6 months, and she built several rainwater harvesting systems out of concrete that worked really well. And obviously the sun's not going to be getting into that, so you're not going to have algae growth. And it's going to be strong. It's going to last a long time. Another one that's really cool is these matrix box ones, and you can buy these. These are proprietary. You can buy these online or probably at some of your nursery systems that specialize in this. But basically, these can be really flexible because you can make them in any shape, and you have an impermeable, relatively strong liner around the outside of a hole that you dig. And then on the inside, you put these crates, boxes. They're kind of like the old milk crates. Very strong. They're designed to be able to be driven over and everything. And as I mentioned, there's a system of these put in at the OSU Botanic Garden. And you know, if you have a regular shaped area beside your sidewalk or whatever, you can use this, and the water goes down in there, and then you pump it out. You have some systems on the front end. So those are really nice. They're a little bit more expensive, but they can be more custom. Than they're out of sight, out of mind, but they hold the water really good for you. If you're looking at them at a larger use, so if you have a commercial development or something like that, these fiberglass tanks that kind of look like long caterpillars or pills, they can get 10,000 to 75,000 gallons. So if you're looking at something that's a really large system, or if you're building a parking garage and you want to have large tanks underground, these are the kind of things that you would use for that. And then finally, our rain barrels. As I mentioned, a rain barrel is not a lot of volume. You're going to run out of it pretty quick, but it's a nice first start. And I think once you get rain barrels, you realize this empties out in like a day, and I need more and more. But they're kind of the gateway into water conservation. So they really serve a nice purpose. There's a couple of videos from Oklahoma Gardening where Kim and I put a couple in at the Botanic Gardens right after I started at OSU back in 2010, where I looked a lot younger. So the next one here is our rainwater sand cistern. And this is kind of, your next presentation is going to talk some about rain gardens. And this is really kind of a combination of a rain garden and a below ground storage system. So you're utilizing sand in the subsurface to store that water here at the Botanic. This is out at the Botanic Gardens as well. And so we put plants on top of there, had some sand columns to encourage the infiltration. And then this is there's some pipe at the bottom here. So we have an impermeable liner, dug a hole, put an impermeable liner down, put under drain pipe with a sock around it, and then have this coming up, and then utilize a electric pump to bring it out. And used our so this is sorted sand. You want to make sure that it's like concrete sand, so that you don't have all the fines, and you have more volume for the water to be stored between the particles. And then you can plant it on the top. And I probably should add a more recent picture because there's water down there. These plants look great all the time. So that's really good. So that's our kind of tanks that we can utilize. Let's talk about water quality a little bit. And you might not think of it, you think of the rainwater, it's really clean, but it's actually hitting the roof right first, the roof first, and anything that's coming off that roof could get in there. So there's some things that we can do to help with that. You may have some metals coming off of your shingles or whatever. Bacteria is one you might not think about, but between storms, you got birds landing up there and going to the bathroom all the time. And so you can have bird droppings up there. Pesticides can actually attach to dust, and you'll get a lot of dust and nutrients actually attaching, or nutrients and pesticides attaching to the dust. And then finally, I did a research project with Jesse, the one who went over to Sierra Leone, on what's called PAHs. So these are actually asphalt compounds, and they attach to the dust as well. And I'll have a couple slides about that right now. So we did some research looking at different kinds of roofs and how much water can we get and what's the water quality that's coming off of them. So we used a metal roof, our sheeting roof, our asphalt shingle, as you would think about, and then some clay tiles that we just happened to get some recycled clay tiles from a La Quinta Inn in Enid. So they were 60 years old, and that was great. And we had a uniform size catchment area, and we did a simulated storm. So it was uniform rainfall for 22 minutes. This was actually out at the agronomy farm up in Stillwater, so it's on the edge of an urban area, and we went 8 days after the last rainfall, and so it was uniform rain. And this is you always say a picture's worth 1,000 words. Well, this is what we saw from that water coming off. So our asphalt shingle, that first part of the storm that came off, that's called the first flush, that was a lot dirtier. And then as you went through the storm, it got cleaner. The next one that was pretty dirty at the beginning was the metal roof, and then finally the clay tile was the cleanest of these. We thought the metal might actually be a little bit cleaner, but I think there might have been some electrostatic kind of things that made the dust want to stick to it or something else. The asphalt shingle is very rough, and so all that dust that's coming in on the wind has a chance to stick up there. But then that first part of the storm is washing it off. And this was, like I said, 22 minutes with an intensity. If it would have rained for an hour, it would have been 2.5 inches per hour. So it was a pretty intense storm. So what can we do to help with that? There are several things. First off, you can get your gutter guard. This is going to get your big debris from going down your downspout, and that's usually your 1/4 inch to 1/2 inch wire mesh or some other type of thing. It's keeping all that big stuff out. The next thing is something that's called a roof washer, and this is right below the top of the downspout, and generally it's a mesh that's at a 45-degree angle or so. The water comes down inside, and the big stuff just falls off the side, and the water keeps going through. And you'll see these in different forms. You can construct them on your own, but they're pretty common to buy. Sometimes they're called a leaf eater. There's different names for them, but these can be really useful for you. And then the next thing that I really like is something called a first flush diverter. And you can either construct these on your own, or you can buy these online as well. And so the water's coming down, and that first part, we saw how dirty that first part of the runoff is that's coming off of the roof. And so if you can intercept that, keep it somewhere else before it gets to the tank, and then just let that go away over the next day, then you're getting, when that fills up, the water's just going to keep going, and then it gets down into your tank. And so then you have this wheat tube that comes out of the bottom of that, and then it'll drain in a half a day or something. And so it'll be empty the next time it rains, but all those particles are down in here. And this one is coming horizontally and coming in. A lot of times you'll see it coming straight down, and I really like it straight down because that water has momentum, and the particles, the dirt and debris that's in that has momentum as well. So even after this is filled up, a lot of times you'll see your particles continue to go down throughout the storm, and then it goes back off into your tank, or a lot of times I'll see the roof washer above it. These are some that you can buy, and I've seen them with these floaty balls in there. I actually usually take the floaty balls out, because what I was talking about with that heavy particles later on in the storm, that ball is blocking those heavy particles from falling down. It's full. The water's keeping that full and keeping it going. So I don't think you really need the floaty ball. I usually take it out because I don't like it. So when we're sizing this, our general rule of thumb is we want to intercept 1 gallon per 100 square feet of the roof. 1 gallon, if you have a 3-inch PVC pipe, is 33 inches. That's pretty long. 6-inch pipe is only 8 inches. So if you have a 500 square feet piece of roof that's draining to your tank, and you want to use a 6-inch first flush diverter, it's going to be 40 inches long, or a little over 41 inches. So that's the general rule of thumb. Part of Jesse's research was testing that rule of thumb, and we actually found that, especially in real storms, that might be a little bit too small. If you're doing something like an organic garden or something like that, you might want to make your first flush diverter a little bit bigger. Part of the reason for that is these were designed and tested, and that rule of thumb was thinking about a uniform intensity storm, which means, it rains the same intensity throughout the storm. Well, that never happens. It might rain really slow for a long time, and then later on it rains really intensely. That slow rain doesn't necessarily dislodge all the particles. But it's a pretty good rule of thumb, and it's still what I generally use for most things, because it's kind of, how important is this to me? What's the risk I want to take, and how much water do I want to have fall away? So how are we maintaining it? First off, just look at it when it's raining. You'll see if it's leaking different places, those types of things. You want to make sure your roof stays clean and your gutters are cleaned out. You can get a lot of leaf and stuff growing in there. I helped put in a pretty big system. I'll actually show the picture here in a little bit, and I'll tell you one of their dirty little secrets is that when we put it in, we went up there to their rain gutters, and they had not cleaned their rain gutters out for so long that there was compost in their rain gutters from all the leaves. So that's really important, obviously. You're going to have your overflow site, so you want to check that for erosion, and hopefully it's designed so that wherever it overflows to, it doesn't have that. But here's the one I was actually talking about. This is a Catholic elementary school in War Acres that myself and another professor here at OU volunteered, and we helped design and put this together. So this is a 1,500 gallon tank. Here's our 3 downspouts. Here's our roof washers at the top, and then first flush diverter. We haven't put the tubing onto this yet to get it. You don't want to have it drain right into the foundation, so we'll put a little piece of tubing so that it drains out a little bit further away. But then it all goes over into this tank, and they actually have an outdoor garden that's for the kids to use to learn how to do that kind of stuff. So this water is going to be utilized for that purpose. I do get the question of, can you use harvested rainwater for drinking water? So the answer is yes, but, and the but is you need to treat that just like it's any other water source. So we're going to, do our stuff with our system, with our first flush diverter and everything else to get all that out. But then we're going to treat it just like if you're getting it out of a pond or a well, you're going to have your filtration. You for sure want to have your disinfection. Anything that you would typically do with any other raw water source, you're going to have to treat that on site so that you make sure that it's potable. So I mentioned that there's a couple things that systems that work pretty cool. We actually installed a pretty big one of these out in Woodward one time about 8 years ago, where you put a catchment out on the landscape and then bring it into this tank. This tank actually has a floating lid on it so that it goes up and down with the water, and there's never any airspace in there, but then the water can still get into it. And then it goes to a drinking trough with like what you would have on any other tank, you know, with the little float on it. So when the trough starts to get empty, it lets some more water in. And that can be utilized for drinking water for your livestock. And then out in West Texas, they've done some other things that are pretty large scale. And these sometimes are even out on game farms where they want to have where they have these places where people come out and deer hunt, so they need to have water sources out there for the deer. And so here you'll see they got funny names for them, but elephant mountain guzzler, black gat guzzler. This one doesn't have a funny name, but this is a concrete catchment. And then it actually goes under the ground, and then there's a tank over here. But once again, it has the catchment, it has the conveyance. It's probably going to have some kind of water quality devices in there that you can see, and then it's coming out into some place where it's using gravity. And then finally, they have some other cool systems that are more smaller, and these can be utilized in the backyard or whatever. Flying saucer guzzler, where they have the water come into this tank and then put it down in there, and they use that for drinking water for birds and things like that. I have a website, greatplainslid.org. In the rainwater harvesting section, I have a link to these, I'm pretty sure. So that's everything about rainwater harvesting. But just in summary, we can collect the water from the roofs, we want to filter it, and we can store it for later on. The important point is, if you don't use it, then there's no space for the next rainfall. And this is like the primary thing about rainwater harvesting is you have great intentions, but if you don't use it, then it's just going to go straight to the overflow every time. So you got to use that, and then maintain it, clean it out. A lot of times I'll see people cleaning them like in August because it's so dry. The tank goes empty if you're utilizing it, and then it's easier to clean it out. So all that stuff is really great. So you can use it for a lot of different things, but irrigation is definitely one that is a good use for it. It provides other short-term and long-term benefits like reducing the stormwater runoff, reducing demands in our urban areas on infrastructure. If you have less runoff, then you have to replace culverts and pipes and things like that. And it can be on a lot of different scales, from a small scale to a large scale. And if you can't do something as big as what this is designed for, do it smaller. But if you're trying to optimize it, then utilize these. But if you have a smaller budget, you just want to get into it and do a rain barrel or whatever, these are guidance to optimize your use. But anything that you can do, you're going to get that water and be able to have some water conservation, provide that good quality water for your plants or whatever use that you want to use it for. So the next presentation is going to be talking about rain gardens, I'm pretty sure. And so I wanted to advertise something that Mike Schnelly and I have been working on now for about 4 years. And it's finally done since before I left OSU. Jerry Fleming, my former colleague here at OU, also helped out, and Alexa Garrison, who was one of our students. And this is going to be about 90 pages, 2 plants per page, of rain garden plants for Oklahoma. And we worked really hard on this, and it should be coming out in the next several months. Will be a hardback book that you can buy online. But we're really excited about this. This will mean more to you after the next presentation, I believe. So I'd be happy to take any questions, or if you guys had some specific applications that you were wondering about or anything like that, let me know.
Not
Brenda, you
seeing,
got a question for me?
I'm not
Hey.
seeing any questions in the chat.
This is Margaret Gebhardt. I'm not sure if you can hear me or not.
Yeah, I can hear you.
Oh, hi. All very interesting, but for my application, I'm just looking for some simple, pretty inexpensive rain catching barrel, etc., from my
Mhm.
house to use in my garden and my foundation plantings, my wildflowers, and
Okay.
so, I've never, what I catch rain in buckets and little, things around the house, but outside. So what do you think is the most efficient, inexpensive way to catch rain, just, from the downspouts, etc., and then be able to use it in my vegetable garden and flowers?
So the inexpensive and efficient might be two different things.
Okay.
But kind of depending on how much, because your tank will be less per store gallon if it's a little bit bigger. And I'm not associated with this website at all, but there's a website called plasticmart.com. It has plastic-mart.com, and they're about the best price for tanks that I've seen anywhere from all the way from small ones up to large ones. And so you can get like a 500-gallon tank for maybe $300.
Okay.
And they actually have a distribution center in Shawnee. So if you need to, you can even go pick it up and save on the delivery.
Right.
And just look for the ones that are available in Oklahoma. But if you're thinking about rain barrels, the cheapest rain barrels that I've seen in Oklahoma, and I love these rain barrels, are at Atwood's. And so you can get a 60 or 70 gallon reused olive barrel, which are those brown barrels with the big black lids, for about $40. And you can connect those together with a pipe if you want to add on to your system. And they come with a spigot on the bottom. And the reason I really like them is because they have a really big lid. A lot of times when you're reusing stuff, it's like those blue Coke things or whatever, they have a really teeny lid and it's hard to maintain them. But this is a big lid that's like a foot around and it screws off. And so when you want to clean it out, you can just take that off and get in there and actually clean it. So that from a small scale, something that's probably available in many towns that have an Atwoods, that's the ones that if I'm buying rain barrels or recommending them to somebody in a locality, check out Atwoods. And I haven't looked at the price this year, but last year they were around $40.
Wow. And they're olive barrels?
Yeah, they're reused olive barrels. They smell like olive oil.
Oh, nice.
And they're brown with a black lid. And they already come with a copper spigot on the bottom. There's some that's actually what we installed in the Oklahoma gardening episode that I mentioned earlier.
Really?
So you can see some of the things that we're doing on that. The important part is when it comes in, you don't want to have any openings that mosquitoes can get in. So if you're bringing it in with a pipe, you can use a hole saw or whatever, and you want to get something that's pretty sealed up. If you're going to take the top off and use a screen, you want to make sure there's no holes in the screen and it can come through there. And that screen can work to divert those particles and those types of things as well. And on your smaller systems, it's probably not going to be cost efficient to do a first flush diverter, if you only have 60 gallons. But sometimes you can even use two barrels together or three, and the first one will collect all those particles, and then you connect it together on the top. So a lot of times I'll connect them together at the bottom with a pipe so that they all empty at the same rate, right? And you get all that storage system. But if you take the first one, put the pipe on the top, that first one fills up and all the particles stay in that one, and then the water empties over from the top into the next ones. So if you have multiple ones, and that keeps all of that dirt in the first one, and the rest of them are really clean then.
Huh. So you could buy 3 perhaps and put them together close to your garden,
Yeah.
and that would be a lot of water.
Yeah. So that'd be, almost 200 gallons.
Yeah, for a
Um,
small garden.
yeah. And so when
Is
you're
there
doing that, you'll generally take like an O-ring and screw it on, so you get that seal really good. You don't want it to leak, obviously. Um, but then just plumb them together.
Is there a site or a fact sheet or anything that I could get that shows me exactly how to do that, put those together?
I would probably just Google around and see what you can find. There is an OSU fact sheet on rainwater harvesting that I wrote a while back. And then as I mentioned, I have this website here, greatplainslid.org, that it has a rainwater harvesting section. And I have a lot of resources linked in that rainwater harvesting section. LID stands for low impact development. So there's information there on rain gardens and rainwater harvesting and green roofs and pervious pavement, and information for other states around the Great Plains as well. But in the rainwater harvesting system, if you really want to get deep into the weeds of rainwater harvesting, Texas has a rainwater harvesting handbook that's about 80 pages long, and any esoteric detail about rainwater harvesting you ever want to find out is in there. But there's an OSU fact sheet and an Oklahoma Water Survey fact sheet that we used a lot of that same information, but I updated it some that we have on there too. Or feel free to reach out to me with an email. And like I said, I'm an administrator now, so I have more pulls on my time, but I still try to get out there. We help that school in More Acres, working through DEQ. But I will say, Oklahoma DEQ has something they call the Green Schools Program. I think that's what it's called, something like that. But if you have an elementary school or a school in Oklahoma that you want to put something like a rainwater harvesting system in, they have small grants to help pay for those. So that one that we put in at More Acres was actually paid for by the DEQ. So if that's something that anybody on here wants to work, or maybe it would be a master gardener project, to help your local elementary school or whatever.
Oh, I'm intrigued by that. What does DEQ stand for? I'm sorry, I don't want to take up a lot of time, but
That's okay. The Oklahoma Department of Environmental Quality. So that's the state regulators from the environmental side.
okay.
But they have a green schools program that's
Cool.
that gives a little money out to schools. There's an application once a year, and the person in charge of that, her name is Sarah Ivy. She's really nice. So she's good to work with.
Okay. Well, it's very helpful. I appreciate it. And I want to move forward on some kind of collection of water. I think that'll be very helpful to my garden.
Great. And are you in Lawton or?
No, I live in Grainfield, so I'm in Tillman County, but I went through the Master Gardener program through Stevens and Cotton County, I guess. Cotton County. But
I'm sure Jamie can help you out now because she's an expert too now, right? So.
yeah, I think
But
so.
Cynthia Williams, who's the stormwater manager for Lawton, I've done workshops for her, and right now with the way the city budgets are, they're probably not doing it. But in the past, they had put on some workshops that I helped them with, where they would give away those 250-gallon cubitaners that are like used in drinking water treatment plants and stuff like that. They would wash them out and give them away, and I would do a workshop for them. And I know they're really in demand now, but they used to be not quite as much in demand. Yeah, sometimes you can find those types of things out there, and they're a little bit bigger, and they have that crate kind of structure around it, and a lot of times will even have a pallet-like thing on the bottom to help you move it around. But that can be 300 or 400 gallons.
Well, I see that I've seen those around greenhouses, and a few people in this town actually have those. And I noticed you didn't mention that.
Yeah, so Atwood sells those as well, and a lot of people love them, and they used to be able to get them for free because they were they're used in like drinking water treatment plants and stuff like that. Some of their chemicals will come in those, and they'd have a whole bunch of them. And now they're able to, people want to buy them from them. They used to like not be able to give them away, but people realize their utility for a lot of purposes. But they do have those on a per gallon basis. They're going to be a little more expensive probably than those olive rain barrel or those reused olive barrels. But those can work really good too, and I've used those on homes, and those work real nice. One thing I didn't mention, but you always want to make sure and have a really strong base and a flat base. And if you're using your rain barrels, sometimes raising it up off the ground a little bit can help you a little bit, especially if you're putting it into your sprinkler cans and those types of things. Because if the spigot's too close to the ground, it's hard to get the water out.
Right.
But you want to make sure and have a strong base, because that water is really heavy. If you have 400 gallons of water, it's going to weigh a lot.
Right. It's like on maybe 4 or 5 cement blocks.
Yeah. Yeah.
Okay.
Or just a full thing of cement blocks on the whole bottom, not just a few of them interspersed.
Right. Yeah.
Depending
Okay,
on the size
great.
of the tank.
Well, thank you so much, Jason. This was very, very informative and helpful.
Great. Okay. Thanks again, Jamie, for inviting me.
You're welcome. Any other questions? If we don't have any other questions, we're going to take like a 5-minute break, go get a glass of water or run to the restroom, and then we'll come back and we'll do the rainwater collection for gardens. I have a Zoom video for that, and it is really it's really cool. I watched it already, so I'll share that when we come back. So we'll come back about 11:10, and we'll go into that video then. So go take a break, and we'll be back. Recording. And we have a video from Qing Lou. I'm hoping I'm pronouncing her name right. Okay, can everybody see that?
My screen is just black.
Just black? Okay, let me see if I can start playing it. Oh, hang on, let's see. Let me try this again, I'm sorry. I thought I had it all worked up, but I guess I didn't have it ready. Oops. Okay, let's go there. Go back here. And there. Here. Okay. Does that pop up anything?
Yes.
Hi, it's so good to be here.
Okay.
I am pre-recording this presentation so that Jamie could display it to all of you on the presentation day, as I will be out of office on that day. And it is late night right now when my house finally quiets down so that I can have a quieter time to get the presentation recorded. Let me introduce myself really quick. I'm going to share the screen now. So for those, for who we haven't met, my name is Qing Lou. The first name letter Q pronounces as if it is a CH. So the pronunciation is Qing, the spelling is QING instead. I am a landscape architecture faculty member at the Department of Horticulture and Landscape Architecture at OSU. This is my 6th year here teaching at OSU. Before teaching, I used to be a practicing designer, practicing landscape architect in the industry. I practiced for 17 years out of college in both Beijing and Boston, Massachusetts. My profession also requires us to be licensed by passing a series of very hard exams, and I'm also a licensed landscape architect. And today I'm bringing you this presentation titled Using Rain Gardens as a Sustainable Device to Capture Runoff and Mitigate Flooding. Speaking of rain gardens, we have to look at this picture. So let's pause for 3 seconds and observe the street. We know that there's a lot of river, and this is a street that is flooded. It is not a channel in the city, not a river in the city. It is actually a street that is flooded. As you can see, there is paving on the other side of this bridge. So what happened for a city to have something like this to happen? And this happened in an Asian country, obviously, but things like this, it could happen anywhere in the world. So the reason that this happened is because the city, the ground of the city is too sealed up. It's way sealed up. And whenever it rains, especially there is a big rain, the water, all these runoff has nowhere to go, and it piled up becomes flooding. Now you may say, we have drains in the city, and we have stormwater pipes that we can drain the water away. Very true, but what if there's a very big rain? What if the city doesn't have enough budget to have adequate of maintenance, cleaning, declogging on the drains, etc.? And what if there's a very big rain? The capacity of the rain, the volume of the rain is way too big, and then the water has nowhere to go but flowing on top of the surface, and whenever there is a slight shallow area, the water will pile up and becomes flood. So at the end of the day, the reason of this is because the city is way sealed up. Let's look at a diagram next. So this is a natural water cycle diagram. Many of us have seen this plenty of times since elementary school, probably. There are 2 movements that I want to point out that is very, very important in this process for us to understand why rain garden is such a great, wonderful mechanism for us to have, for the city to have. Okay, so in this diagram, whenever it rains, there are 2 movements for the water to go. So one is the surface runoff, meaning that the water will flow along the street, along the surface. And there's second movement, which is this one, which is infiltration. That is for the water to flow vertically, which is infiltration, filtered down into the soil and just disappear into the ground. So understanding these 2 movements whenever it rains, it's very critical for us to understand rain garden. So now let's look at this diagram. This diagram pointed out 4 different scenarios. On the far right, it is a very large urbanized city, okay? Meaning that there's a lot of concrete, a lot of asphalt. The surface is very much sealed up. The far left diagram is a park and not much building, not much pavement at all. That means the ground is still very much like a sponge. Whenever it rains, it would absorb a lot of water. Let's look at the data. So here says infiltration, shallow, deep infiltration for a park scenario altogether. There's half of water. Whenever the water drops on the ground, half of the water, 50%, will go into the ground. And only 10% it is flowing horizontally on the surface. On the other end, here in the big city scenario, the infiltration, look at this, 10% plus 5%, that is 15% only versus 50% here, while the surface runoff here is 55%. So that really means that the city is so sealed up, the water cannot filter through into the ground, into the soil. That's why the water has to flowing around on top of the hard paved area. So what if, so this is all of the city happening, all of the cities. What can we do in order to break this cycle and make this scenario more like the other end, this park scenario? Rain garden. So rain garden is a great mechanism that could help to break the seal, to install mini sponges throughout the city, capture the water, collect the water for plants instead of let it flood the city or go into the drain. All right, so let's talk about the definition of rain garden. The definition is very simple, actually. So basically, a rain garden is just a shallow depression on the ground. It's fairly shallow, usually less than 10 inches deep. And this depression usually is planted, and the plants and also this depression usually is located in a lower spot of a property, park or residential, so that it could let water to drain into it, drain towards it. Another word that it'll capture some runoff and to keep the runoff in there. Okay, so that's the definition of rain garden. Rain garden, basically, sometimes it has water in it, especially right after it rains. So this is the ponding occasion. And for a longer period of time, so between rains, most of the time, a longer time, the rain garden could be dry. So rain garden could be without ponding. So let's acknowledge that rain garden can have water, and for sometimes rain garden doesn't have water in it, just the plants. Let's look at the forms for rain garden. So rain garden could be at any shape, actually, when you design it. It could be just a organic shape, kidney shape, figure 8 shape, loose shape like this, or it could have a geometry, as in this picture. This is a more of a rectangle geometry. Having a geometry, having a real geometry, that means you really need to install some sort of a hard flush curve like this one, so that this hard curve could contain the shape that we want to have. But this obviously will increase the cost a whole lot versus this one. We don't need to invest money on the border of the rain garden. But if you would like to design into any shape practically, you can. So that's the forms. Let's look at a rain garden typical section. And here it shows that any rain garden has 3 basic components. Number 1 is inflow. So inflow is the place where the water comes into the rain garden. The second component is the basin. The basin is the depressed area where plants grow. And then there's overflow. For a residential setting or a low cost rain garden in a park setting, a lot of times people just do a berm, just do this berm. And whenever, imagine it rains, and whenever the water ponds up to the height of the berm, and then the water will start to overflow. And the berm is the overflow device, actually. So again, for any rain garden, the basic structure of a rain garden is 3 components: inflow, overflow, and the basin. Now, whenever you want to install a rain garden on your property, in the park, anywhere, we need to understand the design principles of rain garden. Okay, so let's go through that. Usually, the rain garden
Jamie? Jamie?
Hi, Betty.
Hi, it's so good to
Okay. Uh, we have one more presenter. Just waiting for him to pop on here to be able to present. Jim Shrefler is our next presenter. I'm stop recording for a tad bit and we can grab a drink or run to the restroom or grab a quick lunch and we'll come back probably about noon. So you have about 5-6 minutes to do so and we'll start back up then.
You want me to just go ahead and get started then? Or
Yep, we're ready for you.
how many people do we have?
We have 2 others. We had a couple that had started out and then had other obligations. And I have a whole list of people to send recordings to.
Okay.
I probably have 7 or 8, maybe more. I have to double check my list. But quite a few that have wanted recording after it was done. So.
Let me turn the light on here. Okay. Well, let me start off by introducing myself. I'm the area extension horticulturist with the Oklahoma Native Cooperative Extension, and I work mainly out of the southeast part of the state. But I do get involved. I work quite a bit with vegetables, and I do get involved with other activities, vegetable-related activities in various parts of the state. So I've worked a lot with watermelon. So in years past, I used to work out west, some in western Oklahoma with some of the growers out there. So composting is a really interesting topic, and the more that I work with vegetable gardening and growing, the more and more I appreciate composting and the value that it has. It is, when I was growing up, and I grew up in the suburbs in Cleveland, Ohio, and we had lived in a neighborhood where most everybody had a vegetable garden, and most everybody had some sort of compost pile. I'll talk about a little bit more deliberate ways to do composting. But back then, basically, we just had an area, and there might have been an old piece of wire fence that we made a circle out of, and kind of keep a little bit orderly. We just throw everything into that pile, and it would usually sit there 2 or 3 years. We didn't do any stirring or turning or anything to it. I kind of just let it take its own course, and it was actually sometimes part of the garden itself, because there'd always be a few squash plants or a pumpkin plant that would come up there, and maybe some tomato plants, and we just go ahead and use those as they came up there. But eventually, once it broke down far enough, then my father would scatter it out into the garden and maybe use it in the planting hole when he planted tomatoes and things like that. So that's one form of composting. And if any of you that done any gardening have probably at least done some composting of that nature. So, but let me go ahead and pull up my presentation and talk to you a little bit more about some of the principles behind composting and things to be thinking about if you're going to if you want to compost, and especially if you want to produce a little bit larger volumes of compost and produce it a little bit quicker. Because if you provide the right ingredients, make sure you have the right ingredients in the compost, whether it's a pile or bin or whatever, have the right ingredients. If you give it the right management, right more adequate moisture, all you can produce compost pretty rapidly. And it's, like I said, it's, I've come to appreciate it's a very, very valuable material for improving your soil in various ways. So let me go ahead and pull my presentation up here. And if, will we be asking questions during the talk, Jamie, or just pretty much through the chat?
Preferably through the chat, but we only have a couple people, so I asked if they could do it at the end of each presentation. So after everybody had done their presentation, then they were allowed to do questions, or if they put something into the chat, then we can kind of talk about it. If something comes up that pertains to it and they put it in the chat, I'm trying to watch the chat to see if anything comes up during a specific topic.
Okay, please let me know if you do.
Okay.
I have a hard time watching all these little different boxes and things as I
completely understand
here. So let me try and share my screen here. Try to get the slideshow started now. Okay, can you see it? The title is "Why Not Compost?"
Yep,
okay,
looks good.
So, okay, and now these materials again, we have several folks in Oklahoma State University horticulture, and also people in actually composting there's a lot of things involved with it. We have people that are in the ag engineering department that are involved in compost, and others in the plant and soils or agronomy department. So there's a lot of again, when you're talking about composting, there's a lot of different things that it involves. So different people with different backgrounds have some involvement in composting as an issue, the topic. So just what is composting exactly? It's kind of one way to look at it. It's sort of nature's way of degrading organic materials into humus and minerals. You know, you can, when you take just a pile of leaves or other plant materials and all that, you know, what you've got in there is you've got a lot of organic materials that were produced as that plant grew and developed. But within that, while that tissue is living, there's lots of minerals, which you know, basically a lot of different fertilizer elements: potassium, phosphorus, nitrogen, what else? Copper, manganese. You know, all those different nutrients are going to be in that organic material. And as it breaks down, those different things will be released at some point in time in the degradation process. So it's a natural process for returning these nutrients back into eventually into the soil where they were originally absorbed by the plants. Now, when we have a compost situation that is working the way we want it, it's going to be an aerobic situation, which means it's going to be a situation that's functioning with plenty of oxygen all throughout that compost material, and that oxygen is needed for a proper composting process to take place. Okay, if you get it too wet, or if the materials get too packed together, and that oxygen is displaced out of there, the composting process is going to be, it's not going to take place until you get some air in there and you get some oxygen in there and moisture and etc. So this microbiological process, and I say microbiological because the organisms that are really doing the composting are things like fungi and many bacteria and there's going to be a lot of them in there. You know, you don't usually have to add anything to it. That will just be, it'll just things that are in the environment, and when you put all that material there, those organisms will take off and start working on your materials as their food source. So there, some of these materials will be carbon materials, and by carbon, you know, we think of things that are a little bit more woody, papers and things like that. But you know what, I think you know what I'm talking about. Just the dried leaves, for example, would have a lot of carbon in them, whereas green leaves would have not only carbon, but they also have a lot of nitrogen and other nutrients, and some of the other nutrients in them while they're still living in the living state. So again, various species of microorganisms will be involved in this, and very important to have adequate water. You got the compost has to remain moist, and we'll talk later, but not excessively wet either. And then oxygen, and oxygen again is very important. Now this picture is maybe a little bit misleading here, because actually when you get a compost pile going and working properly, while the composting is taking place, you're not going to have a lot of things like sow bugs, and I can't tell what other worms. There might be a red worm there, but actually while that compost is in the process of composting, it'll get pretty hot and it would kill a lot of these organisms. But again, these organisms are very important in the normal recycling of organic materials, you know, just things that fall to the ground and leaf litter and things like that. But when we're in the deliberate composting situation, those things, they may be some around the edge and all that, but right deep down into the organic material that's being composted, you're probably not going to find those. Because it'll be too hot. Now, again, once it does cool down from that intense composting process, then some earthworms and things like that may move in there. So again, why compost? Compost is an excellent and inexpensive way to increase the productivity and workability of the soil. You know, here in Oklahoma, our soils, we have all different kinds of soils. Some of them are pretty easy to work with and manage and be able to till them. And for gardening, we have some other soils that are very challenging with high contents of clays that are not easy to work with. Some soils that are just real sandy, in fact too sandy, because they don't have much structure to them because of there's so much sand. But compost can be added to a lot of these soils to greatly improve their usefulness for gardening. So why compost? What it does is it reduces and recycles yard and kitchen waste to produce an excellent soil amendment, and it's as good of a soil amendment as you can get in any kind of bag that you might go to the garden center and purchase. You know, a properly prepared compost. You really can't beat it as far as something that you can add to your soil to improve it. So and just kind of, you know, why can we compost? Well, from March to October, especially in urban areas, yard waste volumes increase anywhere from 20 to 50%. You know, during the beginning mid-spring or so, and into time when leaves are falling from the trees, lots and lots of organic material is being generated and falls to the ground, and people need to do something with it they don't want it to be piling up in their yard and on their lawns and things like that. So you've got a lot of good material there that's being produced that can be used for composting. Again, it helps the garden, the environment, the pocketbook by composting and putting some of these lawn and garden waste materials to use. And another thing, we had a lady working with us. She went on to a different job, but she was working with composting. And one of the big points she was making is that the environmental problems created by all the trash that we discard, and many of them, you know, many of that stuff, you know, we don't have any choice. There's a lot of things that can't be recycled. at least efficiently and all. But organic materials, yard waste and all that, it just does not make any sense to be putting that kind of stuff in landfills. Once you put it there, you know, it's going to pretty much be there for a long time. We're never going to get any value of it. Whereas if we would compost those kind of materials, we can put them to use immediately in our yard and landscape and all. So what are some of the technical aspects of composting and to get it working properly? Well, again, I've already mentioned carbon and nitrogen. And what probably the biggest, the important number one thing to be thinking about as you're developing your composting system is you want to be sure to have a proper combination of how much carbon and nitrogen materials you have. Now, when I say nitrogen, what I mean is it could be there might be times when you want to, if you think you don't have enough nitrogen, you might even add a little bit of nitrogen fertilizer. But what we mean there is just green plant materials. So green grass clippings would be one thing. And just to give you an example, you know, maybe in the fall, you could be taking some of the leaves that have fallen from the trees, and they're pretty much just carbon. You know, once those leaves die, the nutrients are pretty much get washed out of them. But you could be adding to those leaves some green grass clippings, and those green grass clippings will have a pretty good amount of nitrogen. You know, they could have anywhere from 5 to 10%, really a little more if you fertilize your lawn pretty liberally. You could have some pretty fair amount of nitrogen in those grass clippings. So by mixing those two, you end up getting that right combination of both carbon and nitrogen. And a little bit later, I'll show you if you have too much of either one, that creates problems. So just as an example, 1-to-1 equal volumes of grass clippings with leaves and branches. And again, the leaves and branches are going to be high in carbon, grass clippings higher in nitrogen. But by mixing those two, you get the right combination. There may be, if you happen to have a whole lot of that dry material and you're short on the green material to use, you might want to add a little bit of a urea fertilizer or nitrogen source of fertilizer. And maybe, and here they say 1 pound of urea to a cubic yard of leaves. And a cubic yard is quite a bit of leaves. So with wood chips are going to be a much slower degradation process. One moment, please. I'm going to close the door here. Excuse me, this working at home is challenging. I don't know if you could hear, but I had some children talking in the background a little bit too loud. So, okay. So again, with leaf compost, you want to add some extra nitrogen, and maybe they say 5 parts of leaves to maybe add some manure. Manure would be, if you have a little bit of cattle or horse manure, whatever, that would have a fair amount of nitrogen in it, as well as some microorganisms that would help with that degradation process. Other things you might use to add that nitrogen could be some blood meal, alfalfa meal, a bone meal would actually be more phosphorus, but so. Okay. Now the water aspect, okay. Again, if the compost, whatever your compost situation is, if it gets too dry, that composting process is not going to move along very fast. You know, if you just rely on when it's a rainfall and you're in a dry area, that compost may not stay moist enough for it to be for the breakdown activity to be as continuous as you'd like it. So, so when it comes to moisture, if you reach down into the compost, it kind of ought to feel like a moist sponge. You know, you don't want it sopping wet. The water's dripping off it all the time, so you don't need to be out there watering it every day. But you do want it to have a moist feel to it. So, and again, that last one there would say water runs freely. I guess that's if you pick up a handful and lift it up, and it's so wet that that water runs down out of your hand and down your arm. So. The oxygen, again, as I mentioned, these various microorganisms that will cause the degradation. And basically, what they're doing, they're just feeding on this material. They're breaking down the organic materials. That's their food source. They need carbon, they need nitrogen to be active, and the populations of whether it's the bacteria and fungi and all will build up to real high levels as they're breaking it down. So, but again, for the rapid type degradation, you have to have that oxygen there. Now, if you had a pile that got too compacted and all, and didn't have enough oxygen in it, there are some organisms that will still function under low oxygen levels, but it's going to be a much slower process, and it's probably going to not have a very good odor to it. It may kind of smell bad around the pile, so you really want to have that oxygen there. So again, by restricting the size of the volume of compost that you're working with, they say no more than 5 feet high, 5 feet wide. So you get the idea. I mean, you don't want to, if you make a big, if you made a mound, 10 feet by 10 feet, 6 or 7 feet, which would, you'd have to have a tractor to do that. But that's way on the inside there. The oxygen may not get into there in the composting on the inside. Some of that material may remain uncomposted. Now, you may have seen in some of the urban areas, they have composting facilities where what they actually do is the cities will gather up all the yard waste and leaves and all that. They take them to a location where they make big rows of composting of all this dead organic material, and they come by with in fact they make some special equipment that'll drive over top of those rows and turn it continuously, and they'll do that several times a week, and that way they can deal with a big volume of material and rapidly produce good compost. So that would, but for the yard situation, you don't want to get that pile too big to make it manageable. So, okay, like I said, when you got the right mixture of carbon and nitrogen materials, and you got the moisture and you've got it aerated and all that, once that degradation process really gets going, it'll get really hot in there. Like say, we're talking temperatures of well over 100, and it can be up to 140 degrees. Some of these high temperatures, they can be an additional benefit of the composting process. Is there certain disease organisms and insects and weed seeds and all that you're composting? Some of those, and I'm not going to say all of them, but some of those things actually can be killed by the composting process. So again, if you depending on what you particularly have, if you've got some really badly diseased plant materials and if our disease clinic has told you what it is and they told you to throw it in the trash, it may be that it's something there that even composting would not eliminate all the spores and things like that. Some of the plant diseases have certain spore forms that are high temperature tolerant and things like that. So some of those may not go through that. Some of those may go through that composting process and still be viable, and you put them in your garden, they could create a problem. I don't want you to alarm about that, but if you have a specific disease and they've told you that you need to put that in the trash, I would do that and not compost it. Once so you get your compost going and you want to go in and check that temperature. You could get a long probe thermometer to stick in there to be able to measure the temperature. You can just stick a shovel in, lift it up with a shovel and reach down and feel. And you'll get the idea. When it's 140 degrees, it won't burn you, but it'll feel pretty warm down in there. So anyhow, you can periodically check your temperature. And once the composting process is coming to an end, those temperatures will drop back down. That high temperature will no longer be there because the material's all been broken down. The organisms that break it down, they've slowed down, so you're not generating all that heat. So So again, once your volume of compost temperatures drop down to 100 degrees or so, or cooler, that means it's completed, the process completed. And once it cools down a little more, you'll probably start seeing earthworms move up from the ground below it into the compost and things like that, because there's still good material that they could put to use, so that they could feed on. So the particle size, this is something to think about, especially if you're getting some unusual materials to compost, because it can have a significant rate on the composting. If you, I'm going to just talk rather than going through each of these lines. Some, I've in years back when I didn't have any idea what I was doing, and I tried to do some composting. I remember making one compost pile, and I just put some stuff in there that was too big, sticks and things like that, and I left it a while, and came back 6 months later and dug into it, and all this stuff was, it looked like nothing had happened to it. There were some leaves in there that I put too many leaves in. They just, they just layer up one another, and they don't get moist and all. And they were just dry, they were wet, but they were just leaves that had been there 6 months and hadn't done much. So you've got to think of the particle size. Now, if you break things down, if you can mulch your leaves and chop them up into smaller pieces, they're going to compost quicker. You don't want to be putting large pieces of sticks and things like that. If you have a chipper that you can chip them up finely, that's fine. If you want to just by hand with an axe or whatever, break them up some, that would be better too. But again, you don't want to put really big pieces of things in there. Like I said, they say grind brush and trimmings from your shrubberies and things like that. So those things, if you break them down enough. Now, on the other hand, you don't want particles to be too small. You couldn't get a situation where you come up with, I'm not sure what it'd be, sawdust, for example. A little bit of sawdust would be good to put in a compost pile. But if you get too much real fine sawdust and you put it in there, it's going to get wet, and oxygen, there won't be enough pore spaces for oxygen to get in. And again, you may have a ball of sawdust that sits there for years and really doesn't break down and discard and degrade. So, but again, blend those smaller and larger particles together as you put them in there. And you can do that by, if you're just making a bin type composter, you can put them in there in layers, one on top of another, and continue to alternate those layers. So the quality of compost. Again, the compost is ready to use when those temperatures within the pile, they begin to cool and then remain steady even after the pile has been turned several times. So again, each time you turn a compost pile as it's composting, you're going to be giving it a good shot of access to oxygen and things like that. So after each time you turn it, you may get another heating phase occur. So, but once you can turn the compost and you don't get that additional heating, again, that means that all that material has been broken down to the point where it's not going to degrade rapidly any further. So, and let me go ahead and add right now what another point there. What happens? So we still, say you've had a compost pile going for 6 months and you've been turning it and keeping it aerated and moist and all that. You've got a lot of carbon material in there still. So why would the composting process slow down at this point? Well, you get to a point where you have a lot of you have early on you had a lot of carbon material that was in forms that are readily degraded by those microorganisms, but you get certain other forms of there's a certain other carbon compounds in there that are less susceptible to degradation, and they degrade, but only very slowly. And that's why some of the if you've read about or had any classes on soil organic matter, there's, when you add organic materials to the soil and mix them in, some of those things will break down pretty quickly, but there's a certain fraction of that is very resistant to breakdown. And again, that is what contributes to the true soil organic matter, that amount that is resistant to rapid degradation. Okay, so again, going back to your compost pile, once you've gone through that initial phase and you've been doing everything properly and you've broken the materials down quite a bit, you're going to get to a point where there's some carbon materials there that are just going to be much slower in breaking down, and just not those same organisms that did the initial composting are not going to completely break those materials down in a short period of time. It's going to be a long-term process. So, okay. To prove the handling and quality, there's always going to be some stuff in there after you have finished the composting. You might want to screen it because you may have had a few sticks get in there and things. You may have some clumps of leaves that never did compost properly. So you might go ahead and screen those to get them out and put them back in for the next round, for the next round of compost, and they'll continue to break down there. So. And I'm not sure what the reason for this, but David Hillick, who put this original talk together, he said once you've made your compost, you don't want to go in there and break it down, do things to break it down further. Leave those nice large chunks of compost material there. They help when you mix them into your garden soil. They're going to help add pore space and all that. To improve your drainage and things like that, and aeration of your garden soil once you use those. So kind of go through some of these again, some things I maybe mentioned, but steps to making a successful compost pile. And again, I'm going to say what we say compost pile, but a compost pile can be a lot of different things. And a little bit later here, I'll show you some different types of compost piles, and some of them are not really a pile. Some of them are a different way of containing the material that you're going to compost, but we'll call it a pile for the moment. So the site selection, you want it someplace where you get some sunlight. Again, if you have it in too shady, uncovered area, it may not warm up. It may take a while to get it to warm up enough to where the organisms can really get going. And get started doing the compost process. So area where there's some sunlight, also to keep it from getting excessively wet, if you have some sunshine on it, because you don't want it to be too wet either. So again, you want it to not, if you're especially in town, urban area, whatever, you don't want it to detract from landscape. So maybe you can find an area back in a corner, far corner of the yard or something like that, or behind some shrubbery so it won't be so visible. You want to have it. You want to have a location where it's convenient for adding materials and removing compost, and also doing that. Again, that needs attention. If not probably weekly, at least it'd be good to go out there and do some stirring and all. It's also good, if you can have composting be a family activity rather than just one person doing all the work. That way, everybody, if they're working in the kitchen doing some cutting up vegetables and they have some waste or something, so everyone will know to, when they're finished, take that out and throw it on the composting area to put it to use, rather than just depend on the one person who happens to be there and they see something that's appropriate to be added to the compost pile and they take it. So again, making it convenient, that will make it easier for everybody to be involved. Available water, again, you're going to want to have a hose where you can water it occasionally if things are getting too dry, or when you're just getting compost started and all. And also a well-drained area. Again, you don't want to pick some place where a low spot where where it stays real wet, because that might the compost pile itself may not drain well. It may stay too wet, and again, that slows down the whole process. So the container, again, I'll have some other pics here, containers, but just in general, you want it to be accessible. You want something that will resist decay. If you had something that was made of a really soft wood, or wood that was already half rotted or whatever, your structure may not last too long, because it would be breaking down as your compost broke down. You also want something that allow that airflow. So you see on these walls that they built on this particular unit here, they left spaces between those boards, again, for aeration and water drainage and those sort of things to take place. So So some of the materials, you know, you don't got to go out and spend money on fancy materials. You can get some old pallets. If you have some old poultry wire around and available. If you have some concrete blocks available, you can stack those and make some walls, and again, stacking them so you leave spaces between the blocks, and etc. So now selecting the proper materials to be composted. Okay, what are some of the things that are acceptable? Well, a few that I mentioned already: grass clippings, leaves, weeds, and like I said, the composting process will break down some weed seeds if it's done properly. But you know, all the weed material that you pull out of your garden, you know, crabgrass and pigweeds and all that, there's no reason to throw those in the trash. They're for the most part going to degrade real well in the compost. So go ahead and put those to use if you have a way if you have a chipper or something, you can chop them up. Or if, you know, weeds you pull by hand, you have handfuls of weeds that you go out there pull. All that stuff can be added in there into the compost pile. Some manures, if you have some manure on hand that they're using in the garden, add a little bit to kind of help, more than anything, speed up the process. If you get some, this talk is really not focusing so much on composting manure, but if you do get hold of some manure that is pretty fresh manure, you know, just if you got some from people that have horses or whatever, cows, you don't want to put those manures directly onto the garden. It's much better to compost them. So you could be mixing some of that manure in with some of these other materials in your compost bin as a way to do that composting, those manures. So coffee grounds is another good one. Wood chips, sawdust. Again, these are very high. These are pretty much all 100% carbon materials. So again, keep it. And some of them are pretty. Some of them have their lignins and things in them also that are slower breaking, degrading. So I'd say go easy on these. Don't try to make a compost pile that's 50% wood chips. It'll take a few years for that to really compost well. So other, you know, bark, stems, stalks, what have you, garden and canning waste, and fruits and vegetable waste. So now some things you don't want to use to compost are meats and bones. Again, you may attract rats and things like that you don't want in your yard when you start putting a lot of those kind of things out there. Large branches, again, if they're not chipped or shredded, large chunks of wood, things like that will not, they'll take a long time to break down. So other dairy products, again, probably be attracting undesirable pest animals by throwing those things out there, flies and what have you. So synthetic products, again, no plastics of any sort they're just not going to break down. Even papers that have been, you know, we get cartons that are sometimes have plastic coatings on them. Those are probably not going to, that plastic material probably won't break down. And also pet and human waste is not that's kind of straightforward, you know, just there's risk of having some human pathogens in those. They're not risk, there would be having pathogens in there that could cause disease problems. So, okay. Making the compost pile work. Again, the compost pile is not just a pile of rotting garbage, but a successful pile is structured as follows. So as you put the materials in there, you know, you don't want to just pour a lot of a certain material in there at once. So for example, when you're raking leaves in the fall, you know, you don't want to fill your bin up with just leaves directly, but what you want to do is put a layer of the leaves, put a layer of a green material. If you're short on the green material, put some leaves, a little bit of fertilizer, leaves, a little bit of fertilizer, toss in a little bit of topsoil on top of those. That would occasionally also be beneficial, and that's going to have the bacteria and fungi in it that will get the process going. If you were to pile just a lot of leaves and just a bag fertilizer in there for the nitrogen source, you may not end up having too many microorganisms in there, and it would take a long time for those to get started and built up there. So little bit of soil would be another way. Or if you have some other compost that's not quite finished or whatever, it would have those microorganisms too. So that would be another way. Toss a little bit of that compost with the layers, among the layers of leaves that you put in there. So now they say layers of enriched materials or fertilizer. Various things could be used here. You kind of have to just think about what you have. If you have, a lot of times I find I get a bag of fertilizer and it's been sitting in the back of the garage for a while, and it's kind of gotten junky and all that. And it's not good consistency for spreading on the garden. Sometimes that kind of stuff, you can break it up and use that, toss some of that into the compost pile. Again, sparing, you don't want to put a large volume, but maybe to 10 bushel leaves or something, maybe something like a cup full of a garden fertilizer would be the amount that we'd be talking about there. So then layers of soil again, and the main reason for that is to be adding the microorganisms that are necessary to get the decomposition process moving. So again, doesn't have to be a lot, but just there's just a shovelful. In such as this bin they have here, just scatter a shovelful over that surface as one layer. So, and here you see completed pile, and you can see kind of the layering there of layers of I don't know if I can, dark layers, then green layer. Oh, it backed up on me. I did everything else I didn't want to do. So again, you see the layers there. Okay, troubleshooting. What happens if things don't go right? And like I said, some of my early experience with trying to, once I was off on my own and hadn't learned what I should have when I was a youngster. But sometimes you build a compost pile and it doesn't work right. You get it started and you come back several months later and just nothing has happened, or it has a bad odor, what have you. So if it has a strong odor and it might be kind of a putrid smell, what have you, could be not enough oxygen is getting in there. So again, turn the pile, stir it up. Could also be that it's too wet, and if that's the case, you may just add some dry materials, or by turning it again, also that's going to be another way of getting it to dry out. Again, like I said, when you get a lot of things like leaves in the pile there, they can get pressed together and compacted, and they're wet inside there. But again, you don't have oxygen getting in there for the breakdown to occur. So by stirring that, you'll get the oxygen in there, and you'll get the moisture to where you want it, and then the process will continue. So if the pile is damp but it won't heat, it may be that you're low on nitrogen, so you have too much of the carbon material, not enough nitrogen material. Add some fertilizer, add some grass clippings. If it's or maybe add some dry material too. Again, if it's damp but not heating, it could be that it's staying too wet. So by adding some dry, and maybe if like I said, when you get situation where you get whatever kind of particles or materials you have in there, that they just seem to layer against one another real tightly and stay wet and stick to one another, you may want to add a material of a different texture, maybe a little bit of something like sawdust or what have you, to break up to help create some pore spaces throughout the compost. So if it's dry and not composting, maybe you just don't have enough water in there. Again, maybe you might want to kind of open the pile so you have a low spot in the center, and then in high around the edges. That way you can put water in the center there, and it will soak in the compost rather than running off. If you can have a situation, I think, where say you had a lot of pine material in there, which is real acidic, you could create a situation there where it's too acidic for some of the microorganisms to function properly. So, you know, and if you think you have that kind of situation, maybe a little bit of lime could help bring the acidity up, and then that would allow those microorganisms to function a little bit faster. So, if it has a smell of ammonia, that probably means you have too much nitrogen there. You've added too much green material, what have you, and in combination with that, maybe too wet. So add some additional high carbon material, which would be sawdust or leaves, or what have you, other dry materials, and that might solve that problem. So again, we kind of already mentioned this, but what can be composted? Pretty much anything that originated from plant or animal materials can be composted. So that would be sugars and starches, which, you know, fruit scraps, vegetable scraps, wood, paper, newspaper would be another one. You know, what I'd be careful there, because if you put large volumes of paper in there, it gets wet. It just forms layers, and water doesn't, you know, you don't have pore space in there. You're not going to get oxygen to it. But if you could shred the paper up and mix it in with the other material, something like that, that would be a good possibility. So vegetable oil they had here, I'm not sure. I don't know how much vegetable oil you want, but vegetable materials that are a little bit oily would be okay. I sure wouldn't just go out there and pour your you know, if you cook with vegetable oil, I wouldn't go and just pour that old vegetable oil onto the pile. So, and things that are materials, polymerized plastics and vinyl, and you know, we've got some. There's some plastics now that are made with plant materials, and they are recyclable and degradable and all that. But I don't think those things would be something that you'd want to put in a compost pile. I don't think their degradation would be quick enough to. I could be wrong there, but I think I'd be discouraged from trying to compost some of those materials unless they specifically said that they can be disposed of in a regular compost pile. So again, some examples of some of these materials that I'm talking about. I think it's pretty straightforward, but in the lower left, you've got leaves, or the upper toward the left, some green plant clippings. I'm not sure what, maybe it looks like in the upper right would be some bean or pea hulls. And then the plate in the middle, just, you know, kitchen scraps, coffee grounds, banana peels, so all those things can go in there. Again, just sparingly. I wouldn't, if you happen to get a special on bananas and you made a lot of something other than bananas and you had a big pile of banana peels, I wouldn't just dump them in there. I'd scatter them around. Okay, mix them in with other things too, because if you pile them all together, the more likely when you pile any material together by itself, you're going to have a spot there that you're going to have a chunk of material that is going to be a little bit more resistant to quick degradation, quick breakdown. So some examples, again, of composting pile situations. In the upper one on the left, I think that's just a kind of a big pile, not very tall, but scattered out over the ground. So that is one option. Then the upper right are just, again, different types of bin things situation. And then the lower one is just a large pile of material. This is probably, maybe it's some barnyard manure mixed with hay and straw, whatever, that's been piled out to compost. Again, when you have something like that, you're going to want to be able to turn it occasionally if you want it to compost rapidly, and you would need to have a front end load or something like that to deal with something like that. Now, another option are some of these different type of compost drum units and things that you can find, and I've seen some that are pretty large ones. And again, with these, you can because you can aerate them real easily just by spinning the drum around several times. You can add material easily, add moisture to it. You know, you can make compost in a relatively short period of time. So if you're interested in just, generating compost as quickly as you can for use in your yard and gardening, one of these things might be a good investment for you, worthwhile investment for you. So, and some, again, the one in the lower left there, it looks like it was probably made with just a large polyethylene drum in a wooden frame and all that. Others can be purchased. So I don't have recommendations on any which one to use. I'd look carefully at the cost and all, but these things certainly can be beneficial for if you want to be able to produce compost rapidly. And this is what the final product should look like. Again, if it's been composted properly, and if you started with the right materials, so you don't have large chunks of things, and again, it'll be very rich. You might say, well, it kind of looks like a potting soil. It's going to be much richer than potting soil. You would not want to use it by itself from potting soil because the nutrient levels would be too high in it, most likely. So, but again, you could mix things like this with other materials, with peat moss and things like that, and you could conceivably make your own potting mix type materials with it. So. I think that's okay. A couple of resources we have, and I'll let you just go ahead and pull these up yourself. But again, we have one fact sheet that's specifically on turning compost, the key to making quick compost. Okay, so that's one to take a look at. And again, if you're interested in being able to produce compost real quickly, if you have a lot of materials to be composted, I'd look at this fact sheet. Another facet of this is vermicomposting, okay? And what vermicomposting is making use of earthworms as a way of breaking down organic materials. And again, this is, if you get on the internet, you're gonna find a lot of things on this. It produces compost pretty quickly. Another product of this can be worm castings, which is basically the material that goes through the worms that they excrete, which is a lot of, there's been a lot of work to show that it has some good properties for use as a soil amendment for growing things. In fact, there's people that sell worm castings and they don't sell them cheaply, so you can find those sort of things. And again, haven't worked with them myself, but I think there would definitely be something to them there if you want to approach the vermicomposting. Now that vermicomposting, the reason to do that is not just to get the worm castings, but it's a way to break down organic materials pretty quickly. I will say though that when it comes to composting using worms, you need to do your homework on what materials you want to compost before making an investment in doing this approach. For example, we did some work with, been a few years back here in southeast Oklahoma, with using worms to compost chicken litter or chicken manure, okay, from the chicken houses and all that. And what we found is that stuff is just too strong at the start to be able to put worms on it to break it down. Unless you really dilute it with other carbon materials, it'll kill the worms pretty quickly. So it's so hot, it has a lot of nitrogen all in it. So, but vermicomposting can be done for, I know some of the 4-H groups and all do projects with using worms to break down kitchen scraps and things like that as a way of producing smaller volumes of compost. So anyhow, check out those two fact sheets. I think you'll find those of interest too. And that pretty much this is what I have here. I'd be glad to address any questions that you might have if I can.
Not seeing anything in the chat come up.
Let me ask a question to you folks. And have any of you done any composting already, or do you have some different ideas? I know there's a lot of different methods out there that people are using. Have you tried any other approaches to composting?
Me personally, we have horses and we have a couple chickens and goats. And so what we tend to do is whenever we clean out, like with the stalls and then like chicken coop or the goats, we've started a manure pile on one end and we've kind of just made it longer. And then as it's aged and turned into what looks more like dirt, will incorporate it into a small garden, and I've given it away for people who want it, and they love it. But yes, you need a tractor.
Yeah, yeah,
Because there is a lot of it.
yeah.
That's
Oh, go ahead.
that's what we've done. We've not gone through and turned it or anything like that. It's just kind of sat there for the last 6 years.
Okay, okay. So, but a lot of people, a lot of gardeners will go to a lot of trouble to get hold of manure, because it, again, manure is an excellent amendment for gardening. And when I was growing up, we didn't know as much as we know now, and we would actually just go out to, again, I lived in the suburbs, but we would go out to farms in the area and just get raw manure and take that and put it in the garden. And we've learned since then that that's not a good idea, because there can be human disease causing organisms in there that you really don't want to have right in your garden where you're growing vegetables. So
Right.
If you do put fresh manure on, you want to do it 6 months or so in advance and till it into the soil.
Mm-hmm.
And you put it on there and just plant right away. So but again, composting is a way to that you can improve the quality of manure to make it as a more useful material for use in the garden situation. And if you've composted manure properly, then it's okay to go ahead and put it in the garden as you're planting and all that right away. You don't have to have a waiting period there. So.
Okay. Well, thank you. That was very educational. I hope some other people got something out of it. I did record this, so once I get a link, I will share it out to people, and I can send it out to you as well, Jim.
Okay, thank you. I'd appreciate that.
Yeah, we had a full morning of presenters, and I think it was successful. Like I said, I had a couple of people that left due to other obligations, but they wanted recordings, so I will get that out to everybody. And I thank everybody who participated and their help and their assistance, and everybody that watched to come and learn. And if you have any questions, let me know, and I can direct the questions to who can possibly answer it the best. And I hope to make some more events, whether it's via Zoom or in person in the future. We'll just kind of have to see how this all turns out with the virus and what they tell us we can or can't do.
Right. No.
So
I appreciate you inviting me to visit with you folks today.
You're very welcome. Thank you, Jim. And I will end this meeting, and till we see y'all next time.